on climate intervention research. And myself, I'm Mark von Hobe, and I chair the stratospheric aerosol activity of APARC, atmospheric processes and their role in climate. So this is a joint series organized by WCRP and APARC, and we welcome you to the third session. We already had two quite nice sessions with many talks and presentations. Today and tomorrow, we have fewer talks and more time for discussion. Still, I want to remind you about the timing. Even though it's maybe a bit more relaxed, we still would like you to keep the time allocated to you as you requested it in the registration form. In the chat, I will just post a few things to remind, a few rules, just when I finish here, so you can read that in detail. There will be a couple of mini breaks that will allow you to go to the bathroom, prepare a cup of coffee, tea, whatever. And for questions to the talks, we will not address them spoken right after each talk, but in a short session discussion after all talks in one session are finished. But you can paste your questions into the Q&A box. That's preferred. And then speakers can actually address them and answer simple questions straight away. If you are a speaker, you may not be able to paste or write in the Q&A box. Then you can use the webinar chat, which is also fine. And we as conveners will look at that and try to then bring up the questions in the discussion after each session. And yeah, the recordings from Monday are already available in the folder as I send it to you via email. And the recordings from yesterday's and today's sessions will soon follow, so you can follow that up, and all are on the same page for the discussions we have tomorrow on the different themes. Okay, I guess, Leroy, you can start putting the slides up. And Alistair, you can get ready to speak. And yeah, Alistair Duffy is the first speaker of today in the first session on SAI impacts on global and regional climate. And he will talk about global impacts of high latitude, low altitude SAI in 3 Earth systems models. Alistair, the stage is yours.
Great. Thanks, Mark. Hi, everyone. For those of you who don't know me, I'm Alistair Duffy. I'm a PhD student at University College London. I'd like to thank in particular Walker Lee and Lauren Wheeler. Before I start this talk, they were responsible for running the simulations I'll be presenting in CASM2 WACOM and E3SM. I put some pictures of cloudberries on the left there because I found out, to my pleasure, that Hiller actually is Finnish for cloudberry, which I thought was appropriate. Next slide, please. Okay, so in my view, there are really 2 reasons to be thinking about SAI in the polar context. One is that we might want to be targeting polar change as an aim of our deployments, given the extreme and rapid climate changes occurring in the polar regions and the consequences of those changes. But the second reason to consider it is that actually high latitude deployments might be easier because the tropopause is lower in those regions, and so getting aerosols into the stratosphere might be possible with larger or less novel aircraft. And it's that reason that I'll focus on in this talk and with these simulations. Next slide, please. Okay, so just to expand on that slightly, here are some different kinds of aircraft, and very loosely, when I talk about low altitude SAI, what I really mean is that 13 to 15 kilometer range. 13 is a number which is picked because it's the upper bound, it's the upper certification bound for lots of larger jetliner type aircraft, things like a Boeing 777 that you might take on a long distance flight on holiday. 15 is discussed as kind of a bound for some of the smaller business type jets that exist today. And then as we go much higher towards above 20 kilometers, you're getting into the realm of novel aircraft that would be new combinations of existing technologies to create an aircraft capable of lofting significant payloads up into the tropical stratosphere. And so what we wanted to achieve with these simulations was to answer questions like, can we achieve substantial global cooling using existing large aircraft, injecting in that 13 to 15 kilometer range? And what would the trade-offs look like against more conventional high altitude SAI? Next slide, please. Okay, so we performed simulations in 3 Earth system models, UKSM1, CSM2 Wacom, and E3SM version 3, injecting, as is shown on the right-hand side here by those larger black dots, in the space a few kilometers above the subpolar tropopause. So talking about injection heights of 13, 15 kilometers at 60 degrees north-south. And in this kind of scenario, it only really makes sense to be injecting in the local spring through to early summer. And so we had 12 megatons annually, but split between March to June in the northern hemisphere and September to December in the southern. Additionally, we also ran some shorter simulations varying the latitude, altitude, seasonality, and longitude around those central helicases. I should note these simulations are really the kind of testbed precursor experiments which we performed in advance of what are coming soon, which is the new GeoMIP experiment around Hilla SAI. So those new ones are being run as we speak, but follow a similar strategy to this, except holding temperature to 1.5 Kelvin, as in other new GeoMIP experiments. Next slide, please. Okay, so does this work? Does it achieve cooling? And the answer to that is yes, and fairly consistently in the 3 models. So we see a global temperature drop of something like 0.6 to 0.7 degrees C, relatively consistently for 13-kilometer Hilla SAI in the 3 models, and larger changes in the Arctic region. Next slide, please. And then just to go into that in some more detail, we can compare against what I'm calling conventional SAI, which we can take to be the ARISE simulations. So these are simulations that inject at 21 kilometers at 15 and 30 degrees north-south. And we have those simulations in 2 of these models, UKSM and CSM. And if we make that comparison in terms of the cooling efficiency against ARISE, that's what you see on the screen here. And you see that we get something like a 50% efficiency in the global mean cooling for this 13-kilometer Hilla 13 injection case. But this rises to maybe more like 70% in the case of 15-kilometer injection. So increasing the altitude quite strongly increases the cooling efficiency of these Hilla scenarios. I haven't shown it on the screen here, but we can also test how varying the latitude, the exact seasonality within that spring to early summer season, and the longitude have impacts, and generally they impact this less. So the take-home message from our kind of test of sensitivity here was that it's really the altitude which dominates the impact of changing our strategy. Okay, next slide, please. But, and I think this is a very important but, that metric of the global mean temperature change can be misleading, especially when these scenarios are achieving much more of their cooling in the polar regions. And what I'm showing on the screen here is the fraction of the local, the grid cell temperature change, relative to what that grid cell sees under a conventional SAI, a RISE scenario, scaled by the amount of injection. And you see, therefore, that in those kind of bluey green colors, in the polar regions, actually, we're getting close to 100% efficiency relative to a RISE as we get to a 15-kilometer seasonal injection case. But in the tropics, you have these orangey red colors, and you're seeing actually really quite low efficiencies relative to a RISE, so 20–25% efficiencies. And raising the altitude again increases that efficiency, but we still see very significant tropical intercooling. Okay, next slide, please. We can also ask the question of how much is this a polar intervention versus a global intervention? And I think it's an interesting and nuanced question. The aerosol concentrations peak poleward of injection, and that's what we're seeing on the left here. So across the models, we do see this poleward transport and highest concentrations towards the poles. But if we area weight, i.e. we account for the total amount of aerosol, not the concentration per meter squared, actually the majority of our atmospheric burden is equatorward of the injection latitudes. And that's what's being shown on the right here. So something like 60–75% of the additional sulfate in the atmosphere is found equatorward of the injection locations, i.e. most of this actual forcing, the perturbation of the global energy budget is occurring not in the polar regions under these scenarios. Okay, next slide, please. Finally, we can also assess other impacts, and one which we are particularly interested in is sea ice. I won't talk about this in much detail, but essentially, if we reduce local temperatures in the polar regions, we do see significant sea ice restoration. Here I'm plotting this against the local temperature just to make the point that while the Hiller scenarios do increase here Arctic sea ice area in both the summer minimum and the winter maximum, they do that broadly as we would expect, i.e. the relationship to temperature looks quite similar to how it would look under warming scenarios. So there's no evidence really for any surprising increase in Arctic sea ice area. It increases in proportion to the local temperature. Next slide, please. Lastly, we can also think about some of the important side effects and how those might differ against conventional SAI scenarios. I'll race through these a bit. These really will require longer simulations with more ensemble members to answer some of these questions in more detail. But in the case of ozone, only CSM2 out of our 3 models has the heterogeneous chemistry in the stratosphere, which is required to really capture the depletion effects we might expect. And indeed, in CSM, we do see significant reductions in the Antarctic lower stratosphere ozone. I think there's an interesting question about how those reductions measure up against other SAI scenarios, and that's something I think more work will be needed on in the future. We also can look at deposition, and that's what I've plotted on the right here. And broadly, my impression of the deposition maps is that actually they look quite similar to lower latitude injection scenarios, suggesting that a lot of that spatial distribution of deposition is coming from the background atmospheric circulation. And again, with precipitation, we only had 1 ensemble member for each model here, and so we actually don't have the kind of statistical power to really detect anything except quite large precipitation changes. And that's something I hope to see analysis of in these future GeoMIP simulations. Okay, next slide, please. Cool, so a couple of key points. Across the 3 models, there's quite strong consistency in the global and Arctic cooling achieved by these Hiller SAI scenarios. And at 13 kilometers, you see something like 50% of the change in the global mean temperature relative to the ARISE strategy. But those impacts are much more polar focused. Nevertheless, this would be a global intervention. And so seeing this, I think, as a polar geoengineering strategy is misleading. Okay, thanks though, everyone. And I hope to look forward to questions. I think you're muted, Mark.
That's correct. Thanks. Thank you, Alistair, for this very nice presentation and for keeping time so well. So I remind the audience, if you have any questions to Alistair, you can put it in the Q&A box or in the chat. And so the discussion can start right now. And the next talk will be by Chao He, I hope I pronounced that correctly, on the response of Asian monsoon rainfall to stratospheric aerosol injections. Chao, please go ahead. Thank you.
Okay, thank you, Mark. Can you hear me?
Yes, we can hear you.
Okay, thank you.
Yes, we can hear you.
Okay, thank you. My talk is about the response of Asian monsoon rainfall to SAI. Next, please. Okay. Previous. Okay. Many previous studies have suggested that SAI may lead to a decrease of Asian monsoon rainfall, increasing the drought risks. However, we can infer from climate projection studies that reduction of the greenhouse gases concentration may also lead to a decrease of Asian monsoon rainfall. So a question arises, does SAI lead to a stronger drawing trend over the Asian monsoon region than the greenhouse gases mitigation? Next, please. To address this question, we use 6 models participating in GeoMIP 6. We use 2 different baseline selection methods to evaluate the climatic effect of SAI and solar dimming. And we also use the pre-industrial control simulation to examine the range of internal climate variability. We also make use of the SO2 injection matrix simulations to investigate how monsoon rainfall response depends on the injection locations. Next, thank you. The left panel of this figure shows the changes in summer rainfall due to SAI, solar dimming, and greenhouse gases mitigation for panels A, B, C, respectively. It's interesting that the solar dimming experiment almost exactly reproduces the magnitude of pattern of rainfall decrease seen in the greenhouse gases mitigation experiment. But SAI lead to a much weaker drawing trend of the Asian monsoon region compared with the high emission scenario, SSP5. If we choose the SSP2 scenario as the baseline, we can easily find in panel D that SAI may even lead to an increase of monsoon rainfall over the South Asian monsoon region. So next. It's obvious that the monsoon rainfall changes depends on the baseline selection, and it's easy to understand this phenomenon. Look at panel B. Based on the moisture budget equation, we can find that if we choose a much warmer baseline, such as the SSP5 baseline, the rainfall changes is dominated by the moisture content changes. But if we choose a baseline with the equivalent global temperatures, the changes in rainfall is dominated by the vertical motion of air. So as the primary aim of SAI is to decrease global mean temperature, so we choose the baseline of SSP2 and make a regional average rainfall and calculate the regional average rainfall over the Asian monsoon domain, as seen in panel A. Based on the MME multimodal ensemble mean, we can find that the rainfall anomaly in the SAI experiment is slightly out of the range of the internal variability, and it's higher than the baseline rainfall amount. However, the positive rainfall anomaly in the SAI experiment is contributed by two individual models, that is MPI, the two MPI models. But in the other four climate models, the rainfall anomaly in the SAI experiment is within the range of internal variability and not much higher than the baseline. Next. Okay. In order to investigate the source of the intermodal uncertainty, we draw the changes in the clear sky net shortwave radiation at the top of atmosphere. As shown in panel A, we can find that the reduction of solar insolation is different among different models, especially the relative changes between the equatorial region and the Asian monsoon region. If we make a regional average, if we calculate the regional average, the meridional gradient of solar radiation changes between the equator and the 20 degrees north, we can find that this quantity is a good indicator of the vertical motion changes over the Asian monsoon region, and it further controls the Asian monsoon rainfall changes, as seen in panel B and D. Next, please. Okay, this relationship between the rainfall changes and the meridional gradient of solar radiation changes is further confirmed by the matrix experiments with multiple injection locations. So we arrive at our conclusion. First, based on the GeoMap 6, equatorial SAI is not more effective than the greenhouse gases mitigation in drawing the Asian monsoon region. And second, the intermodal uncertainty of the rainfall changes is closely connected to the distribution of aerosols, and the meridional gradient of solar insolation changes is a good predictor of the rainfall changes of the Asian monsoon region. That's all. Thank you.
Okay, thank you very much, Shao, for this interesting presentation as well. And next, Prabhani Tripathi will talk about polar climate risks of SAI. And yeah, please.
Thank you, Mark. Am I audible?
Yeah, yes, you are audible. We can hear you well.
Hello, everyone. I'm Prabhani Tripathi. I'm a postdoctoral researcher at Washington University in St. Louis with Dr. Rajan Chakrabarty. Thank you for the opportunity. I'll present my ongoing research on the potential impact of SAI on polar climate and the plausible mechanisms of these impacts. Next slide, please. As discussed by all the previous speakers today and in the past 2 days, SAI is deliberately intervening in the climate system to offset global warming by injecting highly reflective particle in stratosphere. It is particularly important to understand whether SAI successfully manages risks in these in the hypersensitive regions like the polar climate, or will it introduce new unintended consequences? Polar regions are particularly of interest as climate model projections are highly uncertain in these regions, and the impact is highly amplified with uh, stronger warming signals, which are faster than any other part of the globe. So it is crucial to understand in the previous slide, yeah, it is crucial to understand the trade-off between the global cooling and the polar uncertainties. SAI can potentially offset some effects like the sea ice melt, the glacier loss, and changes in extremes. However, there are some unforeseen regional effects and uneven cooling which needs to be accounted for. The IPCC AR6 report summarizes it as a large uncertainties of effectiveness, substantial knowledge gaps, and there is still a range of risks associated with deployment. So we have identified different mechanisms of risk in polar climate, like the ice albedo feedback, the atmospheric circulation, oceanic circulation, and polar vortex dynamic. And in today's talk, I'll focus on the polar vortex dynamics. Next slide, please. To quantify these trade-off, we have adapted this risk analysis framework, which helps us directly compare the risk of an SAI scenario against that of a non-SAI or unmitigated warming scenario on a polar climate. To apply this framework, we need to first understand what are the different mechanisms and sources of risk in polar climate. Next slide, please. So let's start with the Brewer-Dobson circulation, which governs the behavior and the circulation pattern in the stratosphere. BDC dictates how long aerosols will stay in the stratosphere and where it will sink. The efficiency of BDC depends highly on the strength of the polar vortex. SAI may alter the strength and speed of this BDC, and depending on different materials and injection locations, there are distinct transport pathways that can be shaped due to its response to BDC and polar vortex. There is still insufficient knowledge of these stratospheric transport, and they are particularly concerning to understand the final sink of these particles. Next slide, please. Stratospheric polar vortex is a large region of cold rotating air at the poles, and the temperature difference between the stratospheric equator and the pole drives the strength of this determines the strength of these polar vortex. However, in a rapidly changing climate, due to sudden stratospheric warming in the poles, it is causing a disruption in the polar vortex, which is resulting in extreme cold weathers in mid and high latitudes, and also warm air intrusion into the colder polar region. Aerosol injections like SO2 can increase this pole to equator temperature gradient, as it is anticipated that SO2 like absorbing particle are going to increase the temperature at the stratospheric equator, and they'll eventually strengthen the polar vortex. However, this effect may not be true for other solid particle candidates, which are non-absorbing or less absorbing in nature. They can also cause aerosol polar burden by directly influencing the strength and behavior of the polar vortex. They can also chemically react with ozone and create ozone depletion, and we need to understand these interactions to quantify the risk. Next slide, please. The vortex is not an isolated phenomena. It is connected to the tropics through the quasi-biennial oscillation. Quasi-biennial oscillation is a reversing pattern of equatorial winds between easterlies and westerlies. And Holton-Tan effect is the teleconnection between QBO and the polar vortex. It is projected that this teleconnection is going to weaken under SAI scenarios for SO2-like particles. However, that is uncertain for other non-absorbing particles. This uncertainty is even highlighted with respect to the injection location and frequency. Next slide, please. The impact of the polar vortex extends all the way to the surface through annular modes. Annular modes are basically a seesaw of atmospheric mass between the mid and high latitudes. The southern and northern annular modes are called as positive when they have like stronger westerlies in high latitudes and weaker westerlies in mid latitude. And a strong polar vortex is important for this positive annular mode. Again, these annular modes are very sensitive to the location of injection, and these can, as a result, affect the storm tracks and the shift in weather patterns in mid and high latitude. Alteration to these zonal winds is more pronounced in a SAI scenario with respect to GHGs. Next slide, please. Apart from all these mechanisms, there are some more critical and long-term consequences of SAI, like the ocean ice belt ice shelf mechanism. In case of SAI, it is predicted that the surface of ocean at the poles will get cooled down. However, the deep ocean will still be relatively warm, and this will cause upwelling of warm water at the poles and a disruption in the polar vortex. There is also hydrological suppression, which is anticipated as a result of SAI, which will reduce the snowfall and the ice sheet mass balance will be disrupted in the poles. There is uncertainties around the ozone depletion at the poles. And arguably, the most severe risk is the termination shock. If for any reason SAI is rapidly stopped while the GHG concentrations are still high, the climate system will experience a rapid temperature rebound, and this rapid shock will result in severe and irreversible impacts on the polar ice. Next slide, please. This is a very preliminary research where we have understood what are the different mechanisms that the polar climate can be affected. And for delicate polar climate, it is very sensitive to injection strategies like the location, the amount, the chosen particle, and the frequency. Our goal is to perform a rigorous trade-off evaluation using the risk-risk framework to compare the specific regional harms of SAI scenario against global warming scenarios. This will help in a informed decision-making and to understand uncertainties before the deployment starts. Thank you. Next slide, please. Thank you. As I have said, this is a very preliminary ongoing research, and I welcome all suggestions and feedback. Thank you.
Okay, thank you very much, Shrabani. I enjoyed your talk, and I think this uncertainty and risk matrix, that could be quite helpful for the later discussion. And the next talk will also address the stratospheric circulation response and changes and how uncertain they are in response to SAI. And that talk will be given by my colleague Mohamedou Diallo. So Moha, please start and give your presentation.
Yeah, thank you, Mark, for introducing. Do you hear me?
Yes, we hear you well.
Okay, perfect. Yes. Yeah, I will talk about the circulation response here due to the stratospheric aerosol injection. So as you can see here, yeah, the climate system is quite complex. You have interactions, and everything is kind of connected. Interaction between troposphere and stratosphere, but all the layers, and also the climate model variability, Kibio and also the chemistry part, ozone, water vapor, and so on. So I thank my colleagues here, and so one of my former master degrees who also contribute to this work. Next, Mark. So just quickly, I will talk about like a little bit of background, but I think I don't need to spend a little bit time on it because there have been several talks covering this part. I jump to the Pinatubo impacts on BDC, comparison between climate models, and then reanalysis, and then talk a little bit about the mechanism and uncertainties on the mechanism, and then the analog of the Pinatubo for the SAI. Next. Yeah. Quickly, just to introduce BDC, is the transport of air masses from the tropical tropopause to the different part of the stratosphere and mesosphere. You have different kind of branches here. You have the shallow branch, which is more driven by synoptic scale wave, and then you have the deeper branch, which is driven by planetary wave scale, and then we have the mesospheric branch, which is go from pole to pole. And as you can see, the mass is transported from the tropics into the different area of the stratosphere, and this actually can be, the metric of this circulation can be derived from what we call the age of air. The age of air will be definitely the time that the air parcels will take to travel from the tropopause once it's left the tropopause to a given area in the stratosphere, and the difference between these 2 points actually give you the time transit. Yeah. Next, Mark. So quickly, I mean, as you know that when you have a volcano, actually it kind of changed the radiative forcing, the incoming solar radiations actually, and then this incoming solar radiation is changed, and then this lead also to a kind of a compensation by the Earth budget of radiation which emitted infrared, and then this infrared actually is also partly absorbed by the aerosol cloud, and then this actually induce a heating and within the aerosol cloud. But you have tropospheric cooling and then stratospheric warming, and then this actually change to the circulation. And you can go next, Mark. And as you can see here, these given ideas actually, if you can take a Pinatubo, it is actually about equivalent, like the Pinatubo forcing is roughly equivalent to doubling the CO2 in the atmosphere. So this gives us actually a hint about what the aerosols can actually lead to the cooling of the troposphere. Yeah. This is actually a time series from Palmer and Stevens, but they kind of go back to most of the volcanoes in the past and showing definitely how they are cooling the surface climate. This actually is kind of the analog what the SAI is doing. But nevertheless, we keep in mind that there is an uncertainties in the representation and interactions of these aerosols and so on with the transport. So go next. Yeah, these are the reasons I think everybody definitely know, like with the climate change, we have the shift of the extreme events. We'll get maybe not more extreme events, but we will get stronger ones. And this actually is a kind of a motivation about using the SAI. Go next. Yeah, so this is coming actually from the recent WMO nice chapter that was really summarizing why we need to do this. But here I want to spend a lot of time. I will just, yesterday there was a nice discussion about the feasibility and the desirability also. And yeah, just to give, yeah, can go next. I think everybody know about this. Yeah, it like the SAI is actually, I mean, it is going actually to offset the climate. As you can see here, the increasing greenhouse gas concentration. Here, this is surface temperatures. This is also coming from the WMO report. We can see that it is going to cool compared to what the climate change is doing if we do nothing. Go next. And it has also an impact on the precipitations, but this is probably the most trickiest part, I would say. It is going to dry several reasons, especially reasons that I consider are the most important, like the Amazonia, the Congo Basin, where also most of the oxygen is produced. This is actually probably one of the, most uncertain one, but it's not only due to the SAI, but probably also due to the fact that the climate models also are always struggling to get the precipitations being consistent over all the models. Go next. The other benefit is also from some studies they show it is going to decrease the extreme related to the fire, the extreme fires, weather events, so on. So go next. This is just for motivation. It has also impact on the circulation. There's a nice paper from Simone where they showed like this is more the residual circulation. What I would say, this is just a pure transport, because this is mainly based on temperatures and wind and then W bar star. They showed that the when you inject aerosols at different regions above the tropopoles, so you can get change of the wind and then change also of the temperature structure. This also lead to change of water vapor and as well as to the chemistry. So though there is what I would say that the SAI impact stratospheric circulation and composition, we've inherited like uncertainties or biases due to the models. Go ahead, Max. So quickly, what we wanted to analyze here was to understand like in what extent the BDC response to the SAI between climate models and then the reanalysis-driven models, how they compare, what are the possible differences, and what are the mechanisms behind, and can you extrapolate the biases from Pinatubo into the SAI, even though we know that the SAI's continuous injections and the volcanoes is a little bit different. Go next. Next. Yeah, we use kind of climate models, EMAC, with several ensembles, and then so-called GeoCCM, and then CLAMS driven with, which is a Lagrangian model driven with like a Fourier analysis, and we look at the age of temperatures, wind, W bar star, and also ozone from observation. And then here the new part is the decomposition of wave into planetary and gravity wave. You can go next, Mark. So we use a kind of statistical framework that allowed us to kind of remove all the other signals, climate variability signals like Kibeo, ENSO, and so on. And then we can clearly focus on what the aerosols actually are doing, how the aerosols are impacting the circulation. Go next. So here, this is just a quickly decentralized age of air in the tropics after the Pinatubo. We can see the climate models, which is in gray here, and then in orange, and then the reanalysis in gray, and we have kind of separated what we call the shallow branch, which is go from like let's say 100 hectopascal to about 70. And then what we call then the deeper branch, which goes a little bit above from 70 to 30 to 10 hectopascal. So what we can see here after Pinatubo, we have a kind of quite a consistent response of the age of air. It is quite increasing in the low stratosphere, but it is kind of deviating. The models, what they are showing, and then the reanalysis, what they're showing, it's an opposite response to that. Mark, next. So when we now just remove what the aerosols are doing, is that what we can see here that the aerosols actually slow down the circulation in the low stratosphere, and then it speed up in the climate models in the deeper branch, but their analysis does not show actually that the deeper branch is speeding. So go next. we try to understand why. So if you are looking just purely at the W bar star, we see that the models and the analysis are consistent. We see a decrease of the W bar star in the low stratosphere, but it is increasing in the deeper part of stratosphere. This tells you that the upwelling below the aerosol cloud is decreasing, but it increases above. So you can get this structure, tell you then the pure residual circulations is increasing above and decreasing below. But it is not the full story. Can go next, Mark. So this is ozone. Ozone tells you also the same story, because ozone in the tropics is definitely correlated with the upwelling. If you have a strong upwelling, you get negative ozone. If you have then weaker upwelling, then you can end up a little bit of not negative ozone, but at least the anomalies will not be that much negative. So you can see here, this is the ozone from at the same time observations, and then the climate models, and then the reanalysis. We can see there is an increase after the Pinatubo, and then at least in the low structures. This is actually consistent that the models and the reanalysis show a slowdown of the shallow branch of the Brouwer-Dobson circulation. Can go next.
You have 2 more minutes more.
Yes, can go next. I think, next. So here, what we see, this is the reanalysis part, which is here on the above, and then this is the climate model. We have wind, temperatures, and then gravity wave. Usually people shows wind and temperature. You can see if you show wind, temperature, and planetary wave, the response between climate models and then the reanalysis are pretty much consistent. But the differences arrive in the gravity wave. We see what climate models actually shows a decrease of gravity wave, also similarly to the planetary wave, and then they increase you get more gravity wave breaking on the upper part, as well the planetary wave, which also explain why the circulation is slowing down and then speeding up above. But the reanalysis show that the gravity wave actually are more, there is less gravity wave activities breaking in the upper part. This actually explains why we get this difference in the deeper branch. So this actually tells us how uncertain the response could be in the deeper branch, because of the gravity wave representation or misrepresentation. You can go next, Mark. Get next. So we extrapolate this to the SAI using here the GLANCE simulation. We have a simulation with greenhouse gases and greenhouse gases plus SAI, and then we make the difference. As you can, and what you can see on the edge of air, you see pretty much the increase of the edge of air all over the place, which tells you actually the circulation is not it is not going faster. It is actually getting slower when you get more ensembles. This actually rules out maybe the role also of the interannual variability in these simulations. So you can see the ozone, pretty much this is consistent with previous studies. We get an increase of the ozone in the lowest part, and then the others decrease, but it is not that significant in the upper part. So next.
Come to an end. Soon.
I think this is
a few seconds.
So then go to the conclusion. I think this is okay. Next one. No, one before. So quickly, just to say that there is a consistent in the shallow branch and consistency on the deeper branch, and the main reason there is due to the fact that there is uncertainties in the internal variability, also in the representation of gravity wave and forcing, not only in the climate models, but also in the reanalysis. You can have also the biases due to the gravity wave representation and forcing, but also the incremental assimilation also may also play a role. So just keep in mind that there is an uncertainty clearly due to the fact of the misrepresentation of gravity wave in either way that give us a completely different response from climate models and reanalysis in the upper part. That's it. Thank you so much.
Okay. Yeah. Thank you, Moha, for this comprehensive presentation on the dynamic response. And next will be Jin Zhu. I hope I pronounced that reasonably well. On stratospheric water vapor response to aerosols in the stratosphere. So please, Jin, start.
Thank you, Mark. Hi, everyone. My name is Xin Zhou. Today, I'm going to talk about the increased stratospheric water vapor after volcanic aerosol injection, which I think is largely neglected as a side effect from SAI. If you look at as it was in the previous studies on climate impacts of volcanic eruption, because if you look at this picture illustrating the climate impacts of volcanic eruption, you can see the water vapor is absent from this picture. Next, please. Until the 2022 underwater volcanic eruption, Hunga Tonga, it completely changed our expectation of the climate impact of volcanic eruption because it injected a huge amount of water vapor into the stratosphere. And our study in 2024, we found this water vapor can stay in the stratosphere for many years, which means it can warm the surface temperature for many years. And it also destroys ozone in the Antarctic. So next, please. Actually, there are two different mechanisms that can produce increases in the stratospheric water vapor after volcanic eruption. The first one is a direct injection, such as Hunga Tonga. The second one is through enhanced transport, for example, the Pinatubo case. So the volcanic aerosol can warm the tropopause, as Moha already talked about the dynamical impacts in the stratosphere. It warms the tropopause and allows more water vapor entering the stratosphere, and this effect can take months or even years. Next, please. Next, please. Previous one. So our study in 2023, we found this increased transport can reach up to 1.39 ppm, which is around 30% of the background level in the tropical lower stratosphere. And this increase is, its peak is occurring in the second eruption year instead of first eruption year. This is actually because of the slow down the rhodopsin circulation after the volcanic aerosol in the stratosphere. Actually, this mechanism I think is very similar to the talk in Moha's studies. So this increase of water vapor in Pinatubo can be very large and they can last for 2 years. So when I was doing this study, I was thinking, can this mechanism also act in the SI case? So next, please. So I used the next, please. So I use the experiments from so the water vapor in the Pinatubo case, it fluxes in, but also it fluxes out. This is why we cannot detect a large increase in the stratospheric water vapor after the Pinatubo eruption, because the water vapor can be dehydrated through the exchange between stratosphere and the troposphere. So you can only see a short-lived increase within natural interannual variability. However, in the SAI case, next please, the warming is from this continuous stratospheric aerosol injection will always be there, and this will cause persistent tropopause warming, which is beyond tropical year-to-year variability. I use the experiments from the Henry et al. 2024 ACP paper. I think this is the same experiments used in the first speaker, Alistair Duffy. The UK-ES1 experiments use a different SAI injection at different latitudes, and we found in almost all different methods, except the high latitude one, the warming of the tropical tropopause are all beyond exceeds the year-to-year variability of the tropical tropopause. This means it will this sustained warming is very likely to drive a gradual increasing water vapor in the stratosphere, and without a clear dehydration pathway in the stratosphere, the water vapor in the stratosphere is going to accumulating in SAI. So next, please. So to conclude, our previous studies we found the volcanic eruption can warm the tropical tropopause through direct aerosol warming and also through circulation adjustment. and this can briefly enhance the stratospheric water vapor entry. However, in case of SAI, this is more important because this continuous SAI sustains this warming, and it will drive persistent moistening without natural recovery periods. So without an effective dehydration feedback, stratospheric water vapor will continue to rise in case of SAI, and this can offset aerosol cooling and amplify ozone and climate impacts from the SAI. Thanks.
Okay, thank you very much, Jin, for the presentation. And the final presentation in this session will be given by Manouk Gertz from the Netherlands, I think. And it's about comparing the hydrological response to SAI and when using solid particles instead of sulfur. So please go ahead.
Thank you. Yes, I'm indeed from the Netherlands. I'm from Wageningen University, and I'm presenting the results of my master thesis, which was about the hydrological response to stratospheric aerosol injection when using solid particles instead of sulfur. Next slide, please. So, well, as you all may know, stratospheric aerosol injection can be used as a measure to reduce global warming and is inspired by the global surface cooling after large volcanic eruptions due to reflection of solar radiation. And to stay close to the inspiration, a lot of the SAI experiments also use sulfur-based SAI. However, there are some undesired side effects associated with using sulfur for SAI, such as its interaction with ozone, but also the absorption with long-wave radiation. And this amplifies the precipitation reduction that is observed with SAI because of its altering of the energy balance, and also stratospheric warming can alter large-scale circulation patterns, and therefore it has been suggested to use alternative materials with less long-wave radiation absorptivity, such as alumina or calcite and diamond dust. And these we will be comparing. Next slide, please. So I first want to explain a little bit more about the relation to the hydrological response and the atmospheric energy balance. So the atmospheric energy balance is basically the energy contained in the atmosphere, which can be written as the sum of the radiative atmospheric energy balance, the sensible heat flux, and the latent heat flux. And the radiative atmospheric energy balance is basically the difference between the radiative balance at the top of the atmosphere and at the surface. And when you assume stable climate conditions, the atmospheric energy balance doesn't really change between two equilibrium states. So then the changes in the radiative atmospheric energy balance can be balanced out by the changes in the sensible heat flux and the latent heat flux. And latent heat flux is generally larger than the sensible heat flux and is therefore more important. And this is how it's tied to the precipitation, because globally, the amount of evaporated water must equal the amount of precipitated water. Next slide, please. And then I wanted to talk a little bit more about the hydrological response, which can be decomposed in two parts. The rapid response, which in the case of increased greenhouse gas concentrations in the atmosphere, causes initially a decrease in precipitation due to increased trapping of long-wave radiation. But on the long term, the slow response is stronger. Therefore, we see an increase in precipitation with global warming, because the warmer temperature causes an increase in evaporation and therefore precipitation. And when we use SAI to reduce surface temperatures caused by greenhouse gas emissions, we only counteract the slow response. So we still see the reduction in precipitation due to the increased CO2 content, and also due to the reduction in incoming solar radiation, and also because potentially the SAI material absorbs also long-wave radiation, which further alters the energy balance. Next slide, please. So how did we compare this? Well, we used the fully coupled atmosphere ocean chemistry climate model, SOCCO version 4, and we followed the experimental setup of the G6 experiments, where SAI materials are injected in the stratosphere to reduce the global mean surface temperature in SSP 5.8.5, a business as usual climate scenario, to the global surface temperature of SSP 2.4.5, which is a mitigation strategy scenario. For each simulation, we had 3 ensemble members, and we had 4 different SAI materials: sulfur, alumina, calcite, and diamond dust, with decreasing long wave radiation absorptivity. And in these experiments, we only use tropical injections. Next slide, please. Now I want to discuss some of the results. First, I want to explain a little bit, because we manually calculated the amount of injected material each decade. There's a slight deviation between the surface temperature of each SAI scenario. So therefore, we normalized we took the difference to SSP 5.8.5, and then we normalized it with the temperature difference between SSP 5.8.5 and the experiment scenarios. And the green bar is then SSP 2.4.5, also the normalized difference of the last 2 decades of the simulation. And what we see for first at the top of the atmosphere, that for shortwave and long-wave radiation, we see the largest difference for the most absorptive materials. And this is because more absorptive materials in the shortwave radiation need more scattering to achieve the same cooling because of the stratospheric warming, and due to the absorption of long-wave radiation. And for the long-wave radiation, it's just a reflection of higher absorption of the long-wave radiation. At the surface, we also see this pattern for shortwave radiation, which is also because of the increased scattering that is needed to achieve the same cooling. But for the long-wave radiation, we see that they are all approximately similar. And this is because the surface temperature is approximately similar, approximately the same. And the difference between SSP 2.4.5 and the SAI scenarios here comes from the different CO2 concentration in the SSP 2.4.5 and the SAI scenarios. And then when we look at the atmospheric radiation balance, FA, we see that for most absorptive materials, the radiation balance is the most perturbed, which is also reflected in the reduction in latent heat, and therefore also in hydrological sensitivity, which is the change in precipitation per degree Kelvin. So we see the strongest hydrological sensitivity for the most absorptive material. Next slide, please. When we look at the distribution, we see that the strongest differences between SAI materials and SSP 2.4.5 occur in the tropics, and this is because of the injection strategy. Here you see the aerosol burden, and because of the injection strategy, the aerosol burden is highest in the tropics, and also the insulation is highest in the tropics, so we see the strongest impacts here. And what we further see is that for less absorptive materials, the changes are less extreme, and also they resemble SSP 2.4.5 more, and this is also what we see at higher latitudes. For example, for sulfur, we see much stronger deviations at higher latitudes from SSP 2.4.5 than for less absorptive materials, and this also suggests that also circulation patterns are influenced, which also influence precipitation patterns at higher latitudes. Next slide, please. Then I wanted to talk a little bit about tropical circulation. So when we look at panel A, we see the tropopause height and the vertical temperature profile, also the normalized difference to SSP 5.8.5. And what we see is that the most absorptive materials have the lowest tropopause height, and this is because the stratospheric heating causes an increase of the static stability in the upper troposphere, so upward motions here are less strong, and this is also reflected in the Hadley cell strength in the tropics, or the Hadley cell strength, I'm sorry, where we see that the strength of the Hadley cell is the most similar for less absorptive materials, especially in December, January, February, and we don't see this clear pattern in June, July, August, and this highlights that not only stratospheric heating is here really important, but also, for example, the inter-hemispheric gradient and the meridional temperature gradient and these are also altered by the tropical injection. So there's need to be looked in further. Next slide, please. So yeah, to conclude, using solid particles with less long-wave radiation absorptivity could mitigate some of the hydrological and dynamical side effects associated with sulfur-based stratospheric aerosol injection. However, we need to keep a few things in mind, because we only consider tropical injections, while previous studies have also already shown that using other injection strategies also reduces impact on circulation patterns. So to fully understand the benefits here, we need to also look into different injection strategies. And also there are still a lot of uncertainties related to using solid particles for SAI, such as its interaction in the stratosphere with ozone. Thank you for listening.
Yeah, very nice presentation. Thank you, Manouk. And with that, we open the floor for discussion. And in the Q&A box, there's one question, or actually, I think it's two related questions. Jerry, do you want to read it yourself? Then someone can hopefully unmute you. And it's, as far as I can see, it's addressed to Tripathi and Alistair, to Shabani and Alistair. But I think Moha also wants to answer that. Jerry, are you still here?
Hi, can you hear me?
Yes, we can hear you.
Yes. My question is to Tripathi and Duffy, but it's more of a general question. The idea I got was that a lot of the simulations of SAI, like RISE, HILA, etc., are a bit detached from the side effect studies. If that is the case, could you explain why is it so, or what can be done to close the gap? Thank you.
Okay, thanks for that question. Maybe Alistair, you start, and then Shabani and Moha, if you also want to give an answer in that order and comment on the question. Thank you.
Sure, thanks for the question. Yeah, I think for me, there's some inevitability to being detached, because many of the side effect studies really require quite specific expertise, right? Like, I'm more of a dynamicist. I'm not going to be able to look at, say, air quality in a lot of detail, but I do think we can do more as a community, and are starting to do it better, to connect up the modelers with the people who'll be using that data. And I actually think these the new GeoMIP simulations of HILA SAI are quite a nice example of that. We did some work to talk to end users who would, for example, want to look at air quality changes, about what variables they needed before we ran those simulations, in an attempt to try and join up those two ends. But yeah, I'll pass to
Yeah, Shrabani,
Annie, yes.
do you want to
Yeah,
say something?
I don't think I have anything more to add, but I agree with Alistair that not everything is possible in one scope of the paper. So it's mostly sometimes very specific to one particular side effect, or if it's a modeling paper, they try to incorporate everything. But yeah, I don't have anything specific to say.
Okay, thank you. And then Moha, you indicated that you want to comment.
Maybe a mistake. No. Yeah, I think I have nothing to add to this.
Oh, okay.
Sorry. Yeah.
Okay, then we can open the floor to further questions or comments. Anyone, please raise your hand, or just speak up. Well, everything seems very clear this morning in all the presentations, but there also, I think there are quite fewer people than in the previous sessions.
You have two people who raised their hand.
Oh, okay. Oh, Gabriel and Alistair. So Gabriel, you go ahead, and then Alistair is next.
Okay. Can you hear me?
Yes, very well.
Hi, Hi, everyone. So I have a question about the talk on water vapor. I believe it was by Jin Zhou.
Yes, that's right.
The speaker is still online. Very interesting talk. I have a question about the dehydration feedback you talked about. Is that feedback namely just the effect of sedimenting ice particles, or how does that feedback actually work? Is it just a general exchange of stratospheric air with the troposphere? So is it basically just a removal of water vapor from the stratosphere back into the troposphere, or how does it work? Can you briefly maybe explain it?
Thanks, Gabriel. So are you asking about the dehydration pathway of the increased water vapor?
Yes.
So I think in the Pinatubo case, the dehydration pathway is very clear from the exchange between stratosphere and the troposphere, and also from the the ice sedimentation from the Antarctic very cold winter. But we need time for this dehydration. In Pinatubo, the increase of the water vapor is gradually increasing in the 2 years, so it gradually fluxes out as well. But in case of the SAI, I think there is no recovery time for this increase of the water vapor, which because the warming is continuously is there because of the injection is continuously there. So that's my base. I think that's the case for SAI.
Okay, thank you.
Yeah, thanks.
Okay, Alistair, you're next.
I just had a question for, I think it was Monique who was talking about solid particles. I was just wondering, you showed some really nice kind of figures that had this sort of spectrum across sulfate to less absorptive particles. Would you be able to comment on, if you had the perfect particle that had no absorption at all, how close that would have looked to the SSP245 case? Like how far is the calcite and diamond case from a sort of radiatively perfect scatterer?
Well, when you use SAI, you always reduce the amount of solar radiation that comes in at the surface. So that will always reduce precipitation because there is less energy for there's less energy that comes to the surface which can evaporate then again. So then there's also less precipitation. So also in solar dimming experiments, you see a reduction in precipitation. So you have two different forcing, because in the case of SSP2, you have a reduction of precipitation, which is because it's colder alone, and because you have because of the reduced amount of CO2. So that's a indirect forcing of the surface. While when you when you influence the incoming amount of radiation, the cooling is the forcing is more direct. So you have cooling because the surface receives less energy, and then also because the surface receives less energy, you also have a decrease of precipitation. So it won't be the same also when you look at solar dimming experiments. Does that answer your question?
Yeah, thanks.
Okay.
Okay, thank you. So we have a couple more minutes before our mini break. Any further questions, comments, statements related to the talks we heard this morning? Jean-Paul, please.
Yes, Mark, thank you. My question is related to Moa's talk on the impact of Mont Pinatubo on the broad absent circulation. He showed that the reanalysis and the climate models are kind of show opposite effect, especially in the upper branch of the broad. And I'm kind of wondering is and Moa mentioned that's obviously the doubts are about the impact of BDC, the impact of volcanic eruptions on BDC, translate also about further doubts about the impact of SAI on BDC, and so the question is, what would be the next steps to kind of reduce those uncertainties, and is it really, I mean, somehow I think it was some connection with Frank Kirsch. Yes, day before yesterday's talk was also talking about age of air, unknown, uncertainty. So how could further research reduce that unknown, and do you think that it would kind of also, some people suggested that doing SAI with other trace gases measurements to allow more understanding of maybe dynamical impact. So what's your position on that?
Yeah, thank you, Jean-Paul, for this very interesting question. So, yeah, I mean, the uncertainties are, especially in the deeper branch, even though without SAI, between the climate models and then the reanalysis-driven simulations, we have a kind of review paper based on the observation, but we have like satellite observation like ACE based on trace gas, that you can read through age of air using SF6, and then MIPAS also. We can still see that the uncertainty is still there, but between the climate models and then the reanalysis. I think one point is the more you go up, the less observation we have. Therefore, it's quite difficult to constrain at the same time the reanalysis, and also have also a quite reliable observations where we can compare also the climate models and then the reanalysis. This is one thing that is really kind of maybe a puzzle that it's still quite difficult to get reliable observation long-term series on the stratosphere to constrain at the same time the reanalysis, because the reanalysis are the closest to the observation, but they are not the observations. They have their biases, and the more you go up, due to the incrementation of assimilation, you get also some induced biases to the reanalysis. And the other way also, you have the models also that has also their own biases due to the fact that the parameterization of gravity wave, we know now the gravity waves are not just propagating vertically, they can propagate obliquely, and they induce also some other kind of additional forcing that is also not considered in the models actually. So I think it's always a trade-off when it comes to the deeper branch. The shallow branch is quite clear how the things goes. You get a little bit more observation, more trace gas that are a little bit more reliable. But I agree with you, maybe more observation of trace gas, like maybe when we have these satellites from that was recently proposed, I think from part of our some of them was part of our team. Mark, the satellite was from Peter, and the others, just the name.
Was it Carrot?
Yeah, carrots, exactly.
Yeah.
Maybe there we can get more different kind of species, then we can get different kind of story about lifetime, and then we can constrain better the circulation between the models and then the analysis, and use these observations like to really see where we get this kind of how can I say it, differences, because we know the gravity wave play quite a very important role, and that's where we see when you take the analysis response, it is consistent with the gravity wave response they have, and then if you take a climate models, they are also consistent with the gravity wave response they have. So then you are in between. You say, okay, where is the right answer regarding the deeper branch? Is it that is it the analysis are right? Or is it the climate models are right when it comes to the deeper branch? Because they show an opposite response, and this opposite response is actually due to the gravity wave break change. This is the puzzle, I mean. So there are more and more effort trying to introduce this kind of oblique propagation of the gravity waves in the models. For instance, I know people in the DLR working on the EMAC try to implement those kind of things. And one other component is the interannual variability in itself. Like most of the models was kind of running 3 ensembles or 4 ensembles. And the more you go in the deeper branch, the time transit is a bit longer. Therefore, you can get also uncertainties about how the aerosols are transported due to the fact that, and also the chemistry is building on this, due to the fact that you have more internal variability, like the polar vortex, you have the TBO that may play a role. You have also, depending on the phase of ENSO, they might also play a role in the wave, how they propagate inside the deeper part. So therefore, at least having more than 50 ensembles can constrain a little bit about the internal variability, and then the left may be then due to the fact that we get uncertainties due to the gravity wave parameterization and also incrementation attenuation for the reanalysis, I think.
Yeah. Okay.
Yeah. Sorry.
Thanks for the question and thanks for the answer. And I think with that, we can conclude this particular session. And after a 3-minute break, we will have an open discussion on SAI impacts, which will cover this session and the other session on global and regional climate impacts on Monday, and also the session on Tuesday on impacts on chemistry, health, and economy. And I may state that it was kind of hard grouping some of these talks in one of these sessions because quite a few addressed both impacts on climate and dynamics and also on ozone. So we open the discussion to the whole topic, and we start that, I would say, at 10:20 UTC, which should be in exactly 3 minutes. Okay, see you then in a few minutes. Thank you. Okay. Welcome back, everyone. And yes, now we have a more general discussion. And Simona has joined by now. And we actually, as organizers, have thought about these discussions and at least prepared a few ideas what could be sort of general questions under these themes. So Simona, maybe you want to kick off with giving us some input so people can start with that.
Yeah, sorry, I did not join the morning session. It was a bit early, but I did look through a little bit through the talks, and it seems like very, very good talks. But this session is not only from today, it's also from the last days when we had impacts, and also a general discussion. So we are a few people, but maybe that's still a really great group to think through some of the questions we had. And we started with some questions to pose to you, but also we want you to think about questions that are most important. Especially thinking about assessments in some way. And I know we have a session later also on the other assessments coming up. But so the questions we had come up with, one question is, what are the largest uncertainties in terms of impact analysis? And I think there was a little discussion earlier that I heard, but I think it would be good to see what people's thoughts are on this and get some input. So I can also read other questions, but let's start with this for now, and then we go to the next question. So do people have a specific feeling for uncertainties that go into these impact analysis? People are thinking. And maybe what I can also do is give you some thoughts on other questions that we came up. We also asking, for example, the question, what can we learn from analogs regarding their impacts? We have heard a lot about analogs, volcanoes, pyrocb, and other places. Is this actually a place or a scenario that we can use to learn from what are the impacts of a potential SAI application? And the last question we also want to discuss is how can we design an impact matrix to produce a risk assessment? And I also saw that a previous talk has addressed this morning. We also have had other presentations the day before that addressed it. And, you know, Mark, I can put those questions in the chat.
You could do that, yeah. Otherwise, we could use the whiteboard feature, but I haven't used it before. So it's under this More button and it says whiteboard, like new whiteboard. I can maybe just click on it. I'm not sure if everyone can then communicate on it.
Yeah.
Oh, Liva can.
Yeah.
So if I mean, that's maybe more visible.
People.
More visible than the chat, but we'll see. But we can also just
the other thing is
talk. I mean, maybe in terms of that impact matrix, I think Shrabani in her talk presented this on one of the earlier slides that already looked quite good, and it would make an excellent start. So maybe Shrabani, you want to comment again and tell us how this work of your group could be expanded by and include maybe studies that other people do. Do you want to comment? Are you still there?
And Mark, maybe the feature takes away the view of the participant.
Oh, okay.
But I know there are many participants not visible that are not panelists.
Okay.
But yeah, it's harder to see. I don't know.
So how I can close the whiteboard, but if we want, we can use it again. So now we can see the video again. I'm not sure, is Shrabani still here? Can't see her.
Here's a comment by Gabrielle in the chat.
Okay.
Gabrielle, did you want to, or was this comment directly to a previous discussion?
Gabriel, do you want to
it was-
speak and just
Yeah.
make your statement? We have more time now, so we can use the floor and use the camera and the mics.
Yeah. So I think if people, one thing I have some thoughts on the impact matrix. For example, the impact matrix includes often, and I try to see, maybe we could look at it again. That was shown in the previous talk. It shows the likelihood of things and the importance of what could go wrong in terms of impacts. But one problem is, it is relative likelihood of events happening towards magnitude of consequences, which is a really good start. But I think many impacts depend strongly on how SAI is actually applied. So having a unilateral deployment will give us very different impacts than if we have impacts, for example, if we have strategies that are global. Then also the polar injections seem to give different impacts than when we have global injections or solar dimming. Again, so this type of difference in terms of strategies, I think, has to be captured in some way. And the problem is also that many people use specific models. One model to understand what are impacts on a certain area. And that's also the question, how big is the uncertainty between different models? And I think somehow, if that could be captured in a matrix, we could do an assessment that could be more multidimensional. So how can we design this? How can we bring in those features?
Maybe Alistair, you want to comment here? Because I know that you have another talk in the later session and that you are kind of thinking into this overarching global direction as well. So maybe you're a person that would be good to give a comment here.
Sure, yeah. I don't want to say too much of what's in the talk because I don't want to waste everyone's time with hearing it twice.
That's okay.
I agree with Simone's points. I think the hard part is definitely capturing those different sources of uncertainty. I think we've been thinking about this a bit in our team at Reflective, as I'll talk about after the break, but it's very difficult to try to pin down sort of graphically a way to represent uncertainties across models, across scenarios, and the fact that the model spread is not the same as our actual uncertainty, and sometimes it's closer to it and sometimes it's further from it. Those things are quite hard, and I agree that that's an important aim, but not an easy one to solve.
Yeah, thank you.
Yeah.
I think, I mean, to identify all the potential impacts and risks of SAI, I think that's very important. And to put some probabilities and numbers to it is equally important. I remember in Monday, when we were in the ethical discussion, there were like some people saying, well, the impacts and the risks of climate change are greater. And then other people said, well, what SAI, it makes things even worse. But I think on both sides, as if we have facts and numbers, then you don't have these washy statements, and you can really say, okay, this is, if we do SAI, this will happen. And if we don't do it, this will happen. And for policymakers, I think that will be the basis for them to make a decision educated by our scientists. And if we don't produce that, they may make decisions without our input, and that may be even worse.
Danielle has his hand up. Do you want to comment?
Yeah, good morning, first of all, everybody.
Oh, good morning, Daniela. Good to see you.
I've been following for the last 10 minutes, but so maybe what I'm gonna say is not gonna be super smart yet, but I think, Simon, I feel like, being explicit about also what are these impacts that are strategy dependent and what aren't, it's important, like maybe being clear about, okay, if you were doing 1 degree of cooling or you were preventing 1 degree of warming, which is a better way to put it, because you're avoiding warming, which ones of the regional or global impacts are very strategy dependent and which one cannot be detected at 1 degree of cooling, with the differences at least between the scenarios and the strategies cannot be detected. And in a way, this is the same problem sort of that the IPCC has had for climate change. And people say, well, but the really local or regional impacts depend on the tropospheric aerosols, and the SSPs capture them poorly, so you can't say anything meaningful. But there's a lot of things that you can say meaningfully for climate change, for what happens with 1 degree of warming. And and the 1.5 report was all about, this is in general across all scenarios, the benefits that you would obtain if you manage to keep warming at 1.5 versus 2 degrees. So it's possible to say, we can't say everything perfectly, but there are things we can say about what would happen under 1 degree of warming or 1 degree of cooling, and then say, of course, at least under a broad category of symmetrical injections versus one hemisphere only injection and so on.
Yeah, so
Okay.
what you're saying is what you're bringing in is another dimension, which is really the amount of cooling achieved, basically, or the amount of warming prevented. And I think that's a very interesting category to bring in, because as we all know, many people look at very strong forcing scenarios to tease out the effect the processes, right? Often you can't really detect changes with 1 degree of avoided warming with SAI. But if you have 4 degrees of avoided warming, you do really actually see something. So we have to kind of categorize that too, the variability is fairly large, and we may not see something that is actually, because it isn't significant, but we need to understand those differences. That's a really good point. The next, I think, Gabrielle, you were next.
Well, actually, there was
Yes.
Greg Slater from the attendees who raised his hand even earlier. So I would have
Yes.
Greg, I would give him the permission to speak first, and then Gabriel. Greg, can you speak, or do I need to?
I think you've
Oh,
given me.
okay, perfect. We can hear you.
Well, my comment was actually in response to something you, Mark, had said earlier before Danielle, and so it's a little bit maybe too late for that, but it was, you had mentioned that on Monday or Tuesday that there was a back and forth between, pro and con on SAI. But I just wanted to emphasize that we are now experiencing in real time actual physical effects of global warming that are catastrophic already. And we are comparing that to hypothetical effects, hypothetical negative effects. I mean, the 0th order effect of SAI is pretty certain, but the hypothetical negative effect, 2nd order effects or whatever of SAI, but are hypothetical. And so it's not a symmetric comparison. We're comparing possible negative effects to known and increasing negative effects on the side of unconstrained global warming. And the second point I would make is that SAI is reversible. Global warming is not on the timescales we would need. So I just want to emphasize the asymmetry in the argument, as I see it, between the potential dangers of SAI and the certain dangers of unconstrained global warming.
Yeah,
that's what I wanted to say.
Yeah, thank you, Greg. I think that some of this goes into the direction that we will have in the last discussion tomorrow. And I mean, we're talking about hypothetical risks, but I think in the impacts discussion, we're focusing on how can we put some more certainty and reliability on these risk assessments. Gabriel, do you want to comment? And you can also pick up where Simone and Daniele left.
Yeah. Can you hear me?
Yes.
Okay. So, I mean, a point I would like to perhaps add to the question of what are the largest uncertainties in terms of impact analysis. I think another factor that needs to be also studied is the, uncertainty in the forcing itself, right? So, for instance, when it comes to not only representation of aerosols in models and so on and so forth, but also the actual, intermittency perhaps of the SAI. So we always think of SAI as something, that we could do symmetrically or asymmetrically. But what about different actors doing different things? For instance, one country starting to do SAI, then ending, then another country starts doing it in the other hemisphere. So basically the intermittency of SAI potentially, that's another factor that should be taken into account, I think, in the future, scenarios perhaps. And that's basically another factor, I think, that maybe we have multiple termination shocks. I don't know. I think that discussion should also be considered.
Yeah, and that kind of, if I jump in, is again the scenario dependence, right? It is the scenario that we are all agreeing globally and do something that we as scientists basically put in place as the optimal SAI scenario. That's one option, but it is a very unlikely one, right? The other one is the reality, and how do we actually deal with that in terms of impacts? Is that what you kind of mean, right? Okay. I don't know if anybody wants directly to comment on each other. I don't know how we do the.
Yeah, I think Jean-Paul and Daniele both raised their hands, and I think Jean-Paul came just a tinge earlier. So Jean-Paul, you start, and then Daniele.
Thank you, Mark. Regarding the impact matrix, I was just thinking that overall, what's the connection between the impact matrix and reducing uncertainties from that matrix? And I feel like always for a long time, we have talked about natural analogs, obviously about SAI, but I think we struggle to connect what analogs can be studied to reduce which uncertainty. For example, I would say, would aerosol microphysics, especially sulfate microphysics, obviously in volcanic plume, seems to be quite a good analog, an interesting analog, at least about SAI, SO2 or sulfuric acid SAI. For example, the dynamics, constraining the dynamics, maybe the pyrocybie and the eating of smoke in the stratosphere affecting the circulation could be another one. So question is, how can we better ties the natural analogs to give processes that needs to be better understood?
Okay, thank you, Jean-Paul. Daniele?
I want to go back and sort of reply a little bit to Greg. I feel like sort of on the other hand of what Simone was describing of the discussion on Monday about, sometimes people do analysis of very high cooling scenarios or really focus on impacts. There is this other perspective that is a bit, but we know how bad warming is and we know how bad warming is going to get. Therefore, we shouldn't really obsess so much about what the potential impacts of SRM would be, because we know that warming is going to be too strong. But this is a bit the limit also of the risk approach in this sense, which is this is a bit the people who were dismissing vaccine hesitancy because COVID is going to be so much worse. And I feel like there is also this point of view of people are going to ask directly what are going to be the impacts of SAI, and we can't just shrug and say, well, but they're going to be minimal because global warming is so bad or it's going to get worse. So there are some limits to the risk. Plus, it is not entirely obvious to everybody that the risk approach is the right one. When we had the UN UNEP WMO meeting in Geneva in May, and one of the panelists spoke about risk, and some of the countries responded, one of the country in particular, I'm not going to name, responded by saying, no, that is not the right way to look at SRM. We should just look at the risk of SRM. Now, I think that country happened to be wrong, but that is a perspective is going to exist. And so you can't always hide that away, and you have to talk about the specific impacts as well. The comparison is going to be useful, but it's not always going to get you away from saying, well, actually, we need to understand deeply some of these impacts. And in particular, this is also and this goes back to sort of maybe also what Jean-Paul and Gabriel were saying. In a way, the other part is, well, what can we say meaningfully about at which point, again, will the impacts be visible, but also at which point maybe terminating a deployment or phasing out a deployment starts to become pretty hard. And that's where constraints over even the lifetime of stratospheric circulation based on observations of volcanic eruption or other information, for instance, I still think that what happened with the shipping emissions in the IMO in 2020 and what's happening with regional aerosols can also be a good indication about what happens when you abruptly remove a source of regional or global forcing and what happens to the climate system. So I personally still think that the IMO 2020 is probably the only near-term opportunity we've had to study what happened in case of a termination, and not many people. It's been quite understudied in a way.
Yeah, and maybe to add to that, Daniela, I mean, when talking about risks of SAI, we're not only talking about some faraway side effects or minor things, but if I understood some of the talks we heard correctly, some of the impacts on dynamics or the hydrological cycle can actually lead to stronger warming in some regions. So it could make things worse. So if we say, okay, climate change, the impacts are so bad that SAI, the risk can't be so high. If we do it in a wrong way, it could actually make the warming even stronger because it has some feedback with dynamics, at least in some regions. So I think we need to be very sure what it does on the climate, right? Simona, you're...
Yeah, a couple of comments. First, I mean, it is surprising to me to see, I mean, it really depends on the strategy. If you see some extra warming in some regions when you do SAI, it really depends on what you're doing, right? If you do polar, maybe you get some extra warming in the tropics or something like that. I don't know. But the other thing that I want to address from Daniela, there is also very interesting results on the reduction of SO2, not only from the shipping, but from the Chinese reduction of SO2. That has been studied recently too. Actually, we saw a couple of studies in a recent meeting. Very interesting how actually the cleanup of aerosols now does lead to some of the warming, not only the shipping that came on top of it. And I'm sure there will be more things that we'll see in the future. So there we go. The climate system is way more complex. It is not only greenhouse gases, it is also aerosols in the troposphere, as you say. And I think my question here was that we want to look at the next step. So Jean-Paul already mentioned we need to look at processes to understand robustly what do we know, how is the climate change, and will it be relevant? And we are doing that already. We do simplified experiments that can be done more, but they are like things like fixing sea surface temperature, as we did, to see what is the impact just on the dynamics, on the chemistry, to do more idealized experiments at this point to really understand how do our models differ. That helps us to reduce these things. And I think we need to go further and really identify in future assessments on what is still needed. Where are really the uncertainties that we can reduce? Because some things we know, if we have the ocean coupled to the climate system, models will give us different answers because the ocean has large uncertainties. But where are the things that we can better constrain? I think that would be one thing we can go and target in for example, assessments or other future documents to go forward with the community and to work together to reduce the uncertainties.
Okay. Yeah, thank you. Moha, you raised your hand a while ago. Mohamedou, can you hear me?
Hi,
You can unmute yourself. Yeah.
Did
Okay, there you are.
Yeah. I
Hi.
think maybe one thing to go comment on what Jean-Paul is saying. I mean the uncertainties. There are things that are still, I can say, some time that we can reshape. Like I mean, one uncertainty about models that I did mention there was the diffusion of the models. Actually, I mean, recent paper from Charles, from part of our group, I think. Charles he was kind of replacing the transport scheme in the climate models, which is usually a random transport scheme by Lagrangian. We can see that we can improve at least the model biases, especially in the low stratosphere. And I think some of the people have shown here, when you inject aerosols in the low stratosphere, you get the transport toward the polar regions. And this actually was due to the increase of the water vapor there and then change the temperature. This is inherent bias from the transport schemes from the models. So if we inject then aerosols with these kind of biases, one also could expect that the biases due to this kind of diffusion of the model in the low stratosphere will also impact the surface response. So there is quite some uncertainties. I mean, that probably could also be reduced by playing with the transport scheme. Nevertheless, also there is some extra tropical volcanoes, some small volcanoes that also have, where we cover also some observations from satellites and so on. This also maybe can also help to better understand how the models response compared to these observed small volcanoes, because up to now, I mean, models have difficulties to agree how much how much amount of SO2 should put in. It is kind of model based, model dependent, also internal variability of the models. And as we know, that the internal variability is actually play a very important role in the models. And when you are doing SAI, you do long-term series, and you're kind of ignoring this internal variability. And the climate change may change the internal variability in itself. It can feedback also to the temperatures and so on. And SAI also is the case. So maybe, the uncertainties regarding transport is, for me, it's kind of a little bit undermined in the way that we say, oh, we put over volcanoes, the circulation is getting faster. And this is not really, this was like an old picture that we have from volcanoes, but this isn't really exact. It's a little bit more complex. You have then some mixing playing in, it's not just pure transport. And then this also will change the temperatures at the surface and will change also how certain regions will respond to the SAI. So that's what I wanted to add.
Okay, thanks, Moha. So we have about 5 more minutes for this discussion. Greg, you want to
Yeah, I would
probably respond again?
Yeah, if it's okay. I mean, I would like
Sure.
to Danielle, even though it's a little bit not exactly what other people are talking about. But again, I mean, Danielle raised the question in particular of termination shock. I think that is an issue which is, I would put that in a different category. That's the longer term issue. But the point I would make is that I don't know of any massive scale project that's ever been done that starts with full deployment without a series of tests being done. And it is crucial that SAI be tested incrementally. There are things like plume dynamics, chemistry, that, as far as I understand, are not sufficiently well understood, and experimentation has to be done. I don't see that it's a scientific position to ban tests that are whose deleterious effects are vanishingly small at small scale. Now, Doug McMartin presented a series of stepwise tests starting from a plane load to a a kiloton or whatever, and at each step, you're looking at the results even before any realistic possible downsides have happened. So, I mean, again, it's this, to me, well, I hate to say pathological, but there is a ban on, there has been a ban on any testing down to the smallest level for decades. And that is not how a scientific development is done. And even though this is a sensitive thing because the potential for downsides, but it has to be approached like that. And at the low end, I don't see the problem of doing that. And the benefit of it is you address some of these uncertainties you're talking about potentially. So there's a great advantage to doing the low level tests, and there is little downside, except for the fact that the climate community as a whole has what I would call a religious ban on even small scale tests in a non-scientific way. That's all I would say about that.
Daniele, maybe you want to answer to that directly.
Oh, I mean, great. Well, I just raised my head towards the end. I don't think, sure, a large part of the scientific community is very wary of the thought of an outdoor small scale experiment. I wouldn't say as a whole, as Doug showed yesterday. So I think that might change, but it is true that there are being calls for bans of even small scale outdoor experiment that do not fit with the history of doing small scale environmental manipulation to understand things like the hydrological cycle. People have added sulfate or nitrogen isotopes to fields to understand the runoff, and so on. So, Greg, on that, you have my agreement. The point is having a plan that makes sense. It is not just we're going to go out and test for whatever reason, but this is what we want to understand better. This is how we're going to modify our tools that already exist based on the observation we take, and that is a multi-year project. I might also agree that the sooner we start, the better, but that goes back to where's the funding, who is interested in doing that, and how do you deal with oppositions from countries that is not just scientists, it's countries as well. Just last week, the French Academy of Science had a report that essentially said also there should be no outdoor experiments whatsoever. It kind of wasn't really picked up much, but they explicitly said as their point one of recommendations, there should be no outdoor tests at any scale whatsoever.
Yeah, thanks, Daniele. Maybe Jean-Paul, and then Simona, you still speak because you raised your hands, and then after that we close this discussion. But we make sure that all these discussions can continue after this workshop in one way or another. So Jean-Paul, you start. Jean-Paul?
You have to unmute, Jean-Paul.
Yeah, and I was about to say my answer has nothing to do with the French Academy decision. But I think one of the reason, I think, to me, that small scale experiments are still too early to implement is simply when you look at what we have done in terms of measurements to study natural analogs, we are still very far away from a comprehensive overview of what has been done. NASA, over the past, let's say now almost 10 years, maybe 7 years, put a response plan after volcanic eruptions to get in situ measurements in those volcanic plumes. But the reality is it's, for the moment, way too costly to deploy an aircraft in fresh volcanic plume. So overall, we have very few in situ measurements in natural analogs. And until we convince research founders that actually we need that measurements, because if we don't get that set of measurements, I don't see how we can go to the next step, which is, I know a lot of people would say natural analogs are a perfect SAI, but still the fact that we have almost very few measurements tells us that the first step before going to do outdoor experiment is to better and make more measurements in those natural analogs.
Yeah, and I guess if I'm the last person to talk on this now, to comment, yes, I agree. We could learn so much more from many things. For example, on the dynamics, sampling volcanic injections from the microphysics. We have learned a lot from Hunga Tonga. Much more could have been learned if we had still more observations. But I think in terms of experiments that we talked about, if we had a government's network, some governance that would actually be able to say, these are experiments that are benign and you can go ahead, and these are not. So we need some kind of body that actually gives legitimacy to certain experiments that people trust. And that's really what it is. The public doesn't trust these scientists that want to pollute them. You know, that's the problem. But if there are so many experiments going on that nobody knows are going on, I mean, we actually could do many things not under the umbrella of geoengineering. We do natural experiments of releasing light with the volcanic what was it, the bombs that were released in the past, and we could follow the material and the transport. I'm not saying that we should do this again, but there are other ways we could do things to really understand transport better, or chemistry. But other experiments, like, for example, Scopex, or suggest that in doing small injections in the stratosphere, I still be really worried that you would never find your sample again, what you're actually releasing. So some things need critical understanding, and it's not only for doing experiments. We may not actually learn something. So there needs to be a review panel, like in all scientific experiments. So yeah, that's just some thoughts. And again, I think since I'm the last, I think this was a great discussion, and I hope we continue this in the future. Thank you.
Yeah, thank you, Simone, for these finalizing
Simone.
words. With that, we close the discussion and the sessions on SAI impact. And we'll take a short break. So maybe we start the next session just a couple of minutes past the hour. And Daniele, you will convene that next session, and Gabriel will be the first speaker. Okay, see you in 3 or 4 minutes.
Okay, I think we can slowly get started. Okay. Hi everyone. Second session today is we have called a special session on SAI assessments and evaluations. And we have two speakers for this session and then an open discussion afterward. So the first speaker for this session is Gabriel Kyoto. Hey, Gabriel.
Yeah. Hi everyone. Hi Daniele. Thanks. So good morning everyone. My name is Gabriel Kyoto. I'm from the Spanish National Research Council, and today I'll be presenting a brief overview of the upcoming Environmental Assessment Panel report, which will contain an entire chapter on SAI effects, broader environmental effects of SAI. And I will be speaking today on behalf of the entire SAI working group listed here. Laura Revel, who is the other lead, Sasha Madronic, also Simone is involved, and others. Next, please. So in the first part of the report, we will focus on the global modeling part. We will use coordinated experiments like GeoMIP and large model ensembles to characterize the general, regional, and global climate effects of SAI, as these are then needed in order to assess the potential environmental effects. So we will definitely report on the existing body of literature when it comes to temperature effects and precipitation, monsoon storm tracks and hydrological cycle effects. Next, please. In the second part of the report, we will actually then focus on the ecosystem effects. So we will touch on terrestrial ecosystems. So here we can name a few potential effects. So with more diffuse, less direct light, we can change photosynthesis and crop yields. This can also impact ecosystems because of changes in the hydrological cycle, for instance, due to changes in soil moisture or carbon sinks. In ocean systems, for instance, SAI can potentially affect circulation and ocean acidification, with potential effects on marine productivity and ecosystems in general. So we need to consider all these effects and also how, for instance, SAI may affect tropospheric ozone and air quality. And finally, in this chapter, we will touch on polar regions, as UV and local climate conditions can greatly affect ecosystems, biodiversity, and so on. Next, please. So one of the highlights in the environmental assessment report will be the effects on ozone, as these are a cause of concern. As historically, we have seen across different generation of models that with SAI, we get depletion in the Antarctic. So the ozone goes down because of heterogeneous chemistry and dynamical effects as well, partly. What we also see is that in the rest of the globe, in the Northern Hemisphere, for instance, the effects of an ozone largely depend on the injection strategy. So we will definitely highlight a paper by Eva Bernards in 2023, testing the impact of polar injections, for instance, showing that in the CSM model, for instance, the Northern Hemispheric ozone actually is less affected. And the ozone effects are key to understand then the broader environmental effects, because the ozone changes determine also partly how UV light will then change in the troposphere. Next, please. Another highlight will be the change in the light quality. So what we know is that, for instance, after volcanic eruptions, the ratio of diffuse versus direct light was definitely increased, as shown in this paper by Zhang et al. In '94. So this is really old stuff, and we know this ever since Pinatubo. We also know that this effect depends on the wavelength, namely in the shorter wavelengths, in relative terms, these change in the ratio is actually smaller because of the ray light effect compared to, for instance, the mid-visible. And so we will definitely then assess also the potential effects of SAI on this ratio. Next, please. And another highlight will definitely be also the use of alternative materials. The question here is, can we tweak the effects on, for instance, diffuse radiation by using different particle types, materials? New work suggests, by Sandro Battioni 2025, published earlier this year, that injecting calcite particles might result in smaller increases in diffuse radiation compared to sulfate. The reason for this is mostly the burden, the smaller burden needed to achieve the same rate of radiative cooling. But both the particle types result also in changes in deposition, as shown on the right-hand side. The changes when it comes to sulfate, for instance, are quite noisy and depend really on the changes in precipitation. A calcite flux, for instance, shown at the bottom, is also largely a function of wet deposition. And in the report, we will also assess the potential of alternative materials when it comes to deposition and diffuse radiation changes. Next slide, please. So another key aspect that we need to assess are the effects on precipitation. But in order to get there, we first need to understand also how the global atmospheric circulation is being affected by SAI. Two major modes of variability that we will report on are the NAO and the SAM in the Southern Hemisphere. The NAO is the North Atlantic Oscillation. And this mode of variability has been shown to actually shift towards more positive phase when doing SAI. And this is robust across 6 different models used in the G6 sulfur basically scheme of CMIP6. And the same also applies to the SAM. When we do SAI, we tend to have a more positive SAM as to when we don't do SAI, and we achieve mitigation by reducing the emissions, such as in the SSP 245, as shown at the bottom. So in both cases, both in the NAO and the SAM, we shift these modes of variability because of doing geoengineering, mostly in the tropics, and altering the temperature gradient and other things I don't have the time to go into. Next slide, please. So ultimately, we want to understand how precipitation is changing, as that is then affecting ecosystems greatly. One reason of concern from SAI is definitely the decrease in precipitation, mostly in the tropical precipitation. And in the assessment report, we will also report the uncertainty across models in this respect. It's also, a reason to highlight that certain regions really see consistently drying, namely the Amazons, for instance. No matter what model you're using, if you're doing SAI in the tropics, you end up having less precipitation in very vulnerable regions like the Amazons or Southeast Asia. Next slide, please. And going beyond just precipitation, what about, for instance, air quality? That will be another topic of discussion in the assessment report. We will report on studies like Eastham et al. 2018 showing the competing effects when it comes to mortality, for instance. What we know, for instance, is that by doing SAI, we may decrease near-surface ozone, but we also would increase PM 2.5, and the two have competing effects on mortality. And there is a great degree of uncertainty when it comes to the net effect in this respect. Next slide, please. And also another point to highlight are the wildfires. We know with climate change, we're going to have increase in wildfires, wildfire weather risk, and generally wildfire burn areas will increase in the future, as shown in the black line at the top. Without doing SAI, it really will go up. If we do now SAI, we definitely decrease warming, and then we also decrease the wildfire risk. There are also, in this respect, competing effects when it comes to, for instance, precipitation, as soil moisture may go down in certain regions, and they may actually partly offset the benefit from doing SAI. When it comes to, again, mortality, there are more recent studies that we will also discuss, showing, again, the competing effects when it comes to a PM 2.5 and near-surface ozone. Next slide, please.
Gabriel, you have 1 minute left.
Okay. So I will try to speed up. So other side effects potentially can be the sky color. We know that, for instance, by doing SAI, we get a whitening of the sky, and also the amount of photosynthetically active radiation So PAR will also change, and they may affect also crop yields. Next slide, please. But again, there are competing effects. There's precipitation, doing something, lower surface temperatures, doing something else, and also the diffuse radiation affecting also plants differently. So it really, when it comes to assessing, you need to also consider the different regions and vegetation types. Next slide, please. And also acidification, as this is actually a problem that SAI cannot solve. Oceans will continue to acidify. Next slide, please. Next slide, I will skip just this one and come to the conclusions, namely that we'll definitely have key statements about potential environmental effects of SAI. We will also make sure that we will be consistent with the ozone assessment with the SAP, which will also be drafted almost at the same time. And our focus will really mostly be on the broader environmental effects, but also encompassing the climate effects, namely precipitation, UV changes, and so on and so forth. And we'll, really make sure we provide an objective assessment, and also may consider using the risk assessment framework. And the report will come out next year in 2026. Thank you.
Thank you, Gabriel. Okay, we move on to the second talk today from Alistair Duffy. Alistair.
Hi, everyone. Thanks, Daniele, and sorry that people have to hear from me again. I'm now talking on behalf of Reflective about an uncertainty and risks database for SAI, which we've been developing. Next slide, please. Cool. So Reflective is a non-profit climate initiative focused on accelerating reflection into research into sunlight reflection, specifically SAI. It's a new organization, and we're looking to do a range of things, including building out a research roadmap. We're funding scientific research, and we're also trying to catalyze a productive conversation about SAI. Next slide, please. And in this talk, I'll be focusing on that first objective around building out this research roadmap. I like this figure a lot. It's from our Scientific Advisory Board meeting report from last year. And this is another example of a kind of matrix, as we saw earlier today. Here we're plotting uncertainties on two dimensions. How big is that uncertainty on the x-axis against how consequential it is on the y-axis? And you'll note, for example, that our Scientific Advisory Board highlighted aerosol size distribution as being of particular importance because it is in a high consequence and also a large uncertainty in this assessment. This was kind of a preliminary assessment of a limited set of uncertainties. What we've been trying to do recently is to build this out publicly as a more comprehensive database of the most high priority uncertainties related to SAI. And so it's that effort that I'll introduce today. And I'd like to highlight that this is available online and we're looking for feedback. So I'll talk more about that at the end. Next slide, please. Cool. So our approach is to consider 4 types of uncertainties. And in particular, of particular importance here is what we're not considering. So we explicitly exclude scenario and socio-political uncertainties from the get-go. We're talking here only about the physical and the engineering side of uncertainties related to SAI. Within that, we drew up these 4 categories. So engineering, including things like the technical feasibility, what kinds of observation we need, etc. Uncertainties to do with aerosol evolution, particularly around the microphysics and chemistry, and also the transport in the stratosphere. The climate response, so things like the large-scale dynamics and interactions with clouds, etc. And then separate to that, the Earth system response that isn't the climate part. So things that are not temperature-driven, for example, those kind of vegetation impacts from diffuse versus direct light that Gabrielle just mentioned. Cool, next slide, please. And to do this, in order to exclude that scenario uncertainty, we draw up a single plausible SAI scenario. And this is what we consider to be plausible. So we define this as being hemispherically balanced, injecting in the subtropics at approximately 21 kilometers altitude, ramping up gradually. So by gradually, we mean less than ½ degree C of cooling in the first decade. That number comes from essentially definitely not cooling faster than we are currently warming the planet, and injecting a gaseous precursor to sulfate. So we're not here either including uncertainties around different materials. in order to talk concretely about some of the engineering uncertainties, we also have to define some aspects of that scenario in terms of timescales, etc. So we have a start date, 2035, which is relevant for discussions about how quickly we could do things like launch certain satellites. And we also imagine that some of the early stage deployment might happen via that HILA type scenario, the high latitude, low altitude scenario. But that we all imagine this would transition to being subtropical 21 kilometer relatively rapidly, so that when we're talking about climate uncertainties, we're talking about this kind of more conventional subtropical 21 kilometer altitude injection scenario. Okay, next slide, please. And one aspect of this that we've taken quite a lot of time to think about, and that has taken some real work on our side, is to try to come up with quantitative metrics to capture uncertainties. And what I mean by that is that, for example, to discuss the aerosol size distribution uncertainty meaningfully, we need to have some kind of number that we can then argue about. So, how likely is it that we are wrong by this much? And so, for example, we might write down, are we wrong by a factor of 2 relative to the current multimodal mean in our effective radius of our aerosols? And at that point, we can then assign an uncertainty characteristic based on saying we think that's a 10 to 50% chance in this example, and we'd give that a medium uncertainty. We then also can define consequence levels, and I can talk about the exact definitions if people are interested, but we define these in terms of the overall efficacy of SAI, or in terms of whether this would change a side effect meaningfully enough to affect overall decisions to deploy. On the engineering side, we generally frame these in terms of like how and when we would be able to deploy. And so in this case, we talk about uncertainties and frame them in terms of things like, would it be longer than 10 years to be able to develop a particular piece of satellite infrastructure? And after we'd had large-scale funding for that. And in this case, we highlight that that's a high uncertainty. We actually don't think we know very well how long it would take to build some of that infrastructure. Okay, next slide, please. Longer term, we're also building out kind of links between these uncertainties and research activities, which would be required to reduce those uncertainties, and with impacts from a sort of human perspective. What is it that people actually care about? Change in appearance of the sky, change in power output from solar PV, for example. And so, yeah, as we go on, we're building this database out to include those links through to those other ways of viewing these same uncertainties. Okay, next slide, please. And yeah, I won't show much of the detail of the outcomes of this, and that's deliberate. This is still a preliminary version, and we've put in a significant amount of work to building out this database, but we're really looking to take in input as we build this. So deliberately, we are sharing this at an early stage because we feel this can only be a meaningful exercise if it uses input from the expert community, including people on this call. But for example, in the current version, we highlight these 4 uncertainties as kind of coming out near the top, either because they have the highest uncertainty or because they have the highest consequence. And neatly, this 4 emerged, one from each of our types. So I'll just say those quickly. We emerged that we think feasibility and timeline for developing satellite infrastructure is a large uncertainty. We think aerosol size distribution is a high priority uncertainty. And then we have one around the terrestrial vegetation response, in particular because of those novel combinations of CO2, temperature, water availability, and different kinds of radiation. And then lastly, there's an uncertainty there around the tropical circulation response, including monsoons and MGO and Walker circulation responses.
Alistair, you have 1 minute left.
Okay, thanks, Dan. Next slide, please. And yes, we're looking for your input. So you can scan that QR code now, or if we share these slides after, there's a link in there. There's also a document that's been shared on the GeoMIP and Geoengineering Google groups. But we are open for comments on this version until October the 15th, after which we'll take those comments away and come up with a revised database. But essentially, we'd like to know if people agree with our methodology for doing this, if they would like to add more uncertainties to our list, whether we are correctly identifying the levels of uncertainty and the consequence we attach to those, and if we're missing important information or references. One more slide, please. Okay, thank you for listening.
Thank you, Alistair. Okay, and this concludes this special session. And if there are any specific questions to the 2 speakers, we can take those. Otherwise, we can just move on to the broader discussion if there's any kind of broader intervention on this topic. I see a hand from Simone. So, Simone, you want to get us started?
Yeah, thank you very much, both of you. This is really interesting and good to see. I have a few comments. Maybe I start with Alistair since just gave the talk. I think one part that we discussed briefly, was it yesterday? I think Seb Eastham presented this really nice paper that we put a lot of effort in with the community, a lot of effort to actually identify uncertainties and also what can be done, right? So what you're showing on the aerosol and just saying, okay, we can do field experiments. We actually went into real detail on that and discussions, long discussions on it. I think having a new version out there that actually starts from the paper we have written, that would be helpful because then we don't need to repeat the same thing that we already done. I mean, that's why in part I haven't commented on it because there is that paper out there and it kind of feels like I don't want to reinvent the wheel that we already done. But I mean, I'm not discrediting how it is organized because that's what we didn't do. And that's what you're doing, is to identify the uncertainties. And yeah, there can be a lot of discussion on what does that mean, medium uncertainty, right? And we try to kind of put criteria there, and I think it is really good to continue this. So yeah, thanks for doing this. And also, I think it would be great to first start from what we already have.
Sure, thank you. Yeah, I hope it doesn't look like we're neglecting the great work that is in Seb's paper because we read that in detail and I took a lot of value from that work. So thank you for taking part in it as well. And yes, I think there's a really important comments that we will try to bear in mind as we go forward. I guess from our side, a bit that I'm really excited about here is doing this in a kind of living way, and that hopefully this can become something that is updated as we go, and that we can make a live document, right? And that is hopefully something that this format is amenable to, that a single paper doesn't do as well as maybe we can by making this something that gets added to over time.
And just as a comment, Simon, if you remember that we did all of that large amount of discussion with Seb for all of that work, but then we were forced to compress a lot of the discussion into just a few phrases, right? And so we know how much work ended up into that, but it maybe is not as immediate to everybody, the level of details that we went into, because that paper ended up being so short when they asked to submit it. So the point of the database is that there's no there's no length limit. So
yeah, that's right. Just to pointing to the appendix that you have to find in the supplement, you do see the tables. That's maybe something you can look at, not just the paper, because that's where most of the information is buried. And I agree with you, Danielle. And so this is really a community effort that you try to do. And that's why we're at the Geoengineering Modeling Research Consortium and all the meetings with GeoMIP. It's a lot of effort to get people to get input, right? And so it will be a long process to continue this. And yeah, I'm really grateful that this is picked up again. Thank you.
okay, Jean-Paul.
Yeah. A comment to Alistair's talk, which I think was really good. Alistair, you said that you did not include political uncertainty and as in the first stage of your uncertainty analysis, which I also found interesting to relate to what's going on right now. Of course, here we know in the US the government shut down, but more like the political uncertainty can have implications on ongoing satellite missions. For example, SAGE, which is probably one of the most accurate satellite observation of stratospheric aerosols, may end in the near future, just because it's not funded in the new president budget here in the US. So, which would have high replications on the metrics, because SAGE provides also as derived products size distribution. So how do you anticipate you could include some of that uncertainty in in your metrics and how this could be implemented.
I think it's a really important point, and thank you, Jean-Paul, for making it. Part of that motivation was just in the interests of practically making progress, and from the type of people that we are as a community, we felt we were more qualified to have a go at the non-political uncertainties, right? Personally, I think those socio-political uncertainties are very, very important, and some of the strongest arguments against doing geoengineering, right, is that side of it. I hope that it's still useful to do the former because other people will do the latter, and then we can combine the two, right? And I definitely don't think longer term we are against potentially expanding this to include some of those uncertainties. But yeah, it was really in the interests of making progress practically. We excluded them for now.
Thank you.
Simone, you want to?
Just a quick comment to that too. I think that's a great start. And I do think also it would be good to aim for the contrasting part too, because it will add a lot. And that is really what people are most concerned about. So as we said, an optimal strategy maybe really way less impacts than a non-optimal strategy, like a single actor and things like that, termination shock, things like that. They have been studied and they lead to large concerns and impacts. It has to be raised eventually. I do agree, though, that you have to start somewhere, and we as physical scientists want to assess what would be the most optimized thing. And I think it does give a political message, because if you say, if we all work together, if we could do something good with maybe SAI, it's an important message to bring forward. If it's ever happening is a different question. And maybe since I want to also bring that to Gabrielle's presentation. I mean, I'm part of it, and I'm actually quite impressed how you put this all together at this point. I think I missed some of the really nice overview and conclusions in the last couple of months. But yeah, just one point to make, for example, or questions, when you did raise the point on precipitation shifting, I think that's another example where all the models at that point, the G6, I think, injected in the tropics and did not use a feedback controller. And that is where you cannot say, well, precipitation is definitely reducing always over these regions. It's just that all the models followed a certain strategy. All the models could have done a better strategies if we had put the work into to implement like a feedback controller in all those models, but of course we didn't have that. So that's a caveat that I think is really important to discuss. The reason why we see those changes is because the models do a certain thing.
Yeah,
Maybe
I agree. I mean, we always have to also consider that a feedback controller is a model world in the end, right? So how realistic is the feedback controller in the real world? Yeah, it's always a question. But yeah, I agree with you that definitely precipitation is largely a function of the injection strategy as well. And that is definitely something we will highlight.
Okay. I see that the chat is just passing up a few links and papers, so I can see any specific question. If there's anybody from the audience, here's an oh no, sadly. If there's anybody from the audience that has a question, or I actually have a comment on Gabriel, something you said, because I am very pleased to see that you pointed out the fact that the difference in diffusion and reflection would be wavelength dependent, because it's something that I tried to put in 2 or 3 proposals and to study a bit more. And I would say even more than the than the visible and the mid visible, this effect would be even stronger in the near infrared, which plants do use to understand where sunlight is and how to grow. And I've always been very curious, and there isn't too much research in these. And actually, I would say we have a proposal that through the Environmental Defense Fund that Ben Kravitz just got accepted, where we're trying to use pyro-CBs as a proxy to try to understand what happens to diffuse radiation at different wavelengths, and then probably try to understand what the impact of that could be through ecological modeling. And it's still very, we still haven't done it, but I think it's really an important thing to point out, the wavelength dependency.
Yeah, I agree. There's not a lot of literature about this. And I mean, the problem you have is that you really need detailed modeling and dedicated modeling to study the wavelength dependence of this. So for instance, in this assessment report, we are lucky to have Sasha on board, and we may be doing some dedicated calculations to also look at, you know, the UV changes and again, right, really studying the radiative transfer in more detail. And you always have the problem with the models, right? In the global models, you don't have output, which is spectrally resolved. Not always, or maybe only in some models. So yeah, definitely there's more to be done in this respect.
Yeah, and even if in the model, well, in CSM, for instance, there is spectrally resolved, but then the way the information about radiation is transferred to the land model is just direct diffuse, visible and near infrared. So there isn't any specific detail for wavelength, because there is nothing, because nobody in the land model, there's no parametrization in the land model to differentiate between the difference between those. Yeah.
Yes. Yeah, absolutely. There's more work to be done in this respect, for sure.
Simone, feel free to speak.
Yeah, one thing, I think this session is on discussion and SAI assessments and evaluation. And my question also is in general, which needs to discuss with the broader group. Where do we go from here, basically, afterwards, and especially with WCRP Lighthouse activity in terms of assessment? I mean, there is certainly it's always good to have a point in time where an assessment happens. So it's good that this assessment happens that Gabrielle is describing. And I think, I don't know how much we, in this assessment, gonna give recommendations for next step and process understanding, potential for experiments. Usually these assessments are just recommendations or summaries. They don't usually give the freedom on saying this is the way forward to research. Or, you know, you can give recommendations, but you cannot say we need this to go forward. But I do think that this activity, the WCRP Lighthouse activity, does not need to follow those constraints. And we could have maybe something that Alistair is somewhat starting also, a living document and progress that can be, of course, at one point summarized as an assessment or a new assessment, but it really collects the question on where do we need to go next. Like Danielle, you have a proposal on radiation, right? That may be a new topic that needs to be discussed, that the land models have to be updated for really understanding. Maybe we need field experiments that can be small, that can look at radiation effects, and in all those areas. And having a living document that starts teasing out all those areas, maybe something that we could go forward with this activity. But it's just a thought, and that's what I want to bring up for this group to discuss.
Yeah, Simone, I think you make a very good point. And I think, I mean, just to mention, together with Gabrielle's assessment, there's also going to be the IPCC chapter that includes SRM, but and we haven't even started writing that yet, so that's going to be far in the future, at least 2026 8. But I agree with you that I mean, two things, the things you said, I especially agree with the fact that, yes, all of these assessments can never make policy relevant recommendations for the way the assessments are structured. But this doesn't mean that, for instance, the WCRP couldn't, or at least the Lighthouse activity couldn't, if that's part of the interest. And the other part is that ultimately doing these assessments, they're always in a way frozen in time, and then by the time they come out, there's already other work coming in, and so the idea of having a living assessment, I mean, not to like we had a paper on these and proposing a living assessment that could also integrate and highlight how maybe doing an outdoor experiment or a new set of measurements would affect uncertainty. I think it's a great idea. So I think in terms of what the WCRP could do, I feel like, you know, some of what you propose in terms of thinking about metrics that more holistically and comprehensive can quantify impacts and uncertainties, I think it would be a really interesting thing. And on top of that, yes, also maybe coming up using that as a way to come up with some form of recommendation about at least what would be the merit of more outdoor tests. And just to answer to Jean-Paul from before, I would say I see personally, I see this as a good way to also raise the salience again of doing a lot of different observations from small volcanic eruptions as a way to say, probably there are going to be some specific details where if you want to really look at aerosol nucleation in the stratosphere, maybe a volcanic eruption is not the greatest analog just because there's other material being co-injected and there's other complications because the plume is going to be hotter and so on. But in a way, if you devise new methods of observing small plumes, or if you explain how important it is, that also is something you can use to leverage increasing the funding when it comes to analogs. But I see that, Jean-Paul, you have your hand up, so.
Yeah, and maybe I can talk about that after, because I was kind of trying to wanted, and maybe Mark can also comment after that, coming to the this workshop effort is really something that Mark has also and you have put together between the Lighthouse activity and the new APAC Stratospheric Aerosol activity. And we also on, and I think it's great because I think in the past, maybe GeoMIP, I mean, if I look at maybe GeoMIP or some other activities, we're kind of little bit disconnected from the CIRC, which is the precursor of SAI. CIRC was really mounted, yeah, more than 10 years ago, 12 years ago, to study how to stratospheric aerosol, mostly, I would say, with a strong observation-based focus, not only, but and so now and our activity is kind of trying to put together a white paper to kind of summarize what are the observations currently available, past observation, present observation, and future. And I think there is obviously a lot of connections with SAI, and that's why we are here today. But in terms of assessment, I think for SAI related assessment, there would be a living document where you can also update what's going on in terms of observations is really important because it's very dynamical. I mean, in 6 months from now or less, maybe SAGE would go and will not have solar occultation. And I think if there is no good ongoing right now platforms for observing stratospheric aerosols, it's obviously a very weak and point to kind of promote even SAI injections if we are not able in the near future to continue stratospheric aerosol observations from solar occultation. So I think the connection with the living document you are referring and the assessment of stratospheric aerosol observations kind of going in the same direction. And I think we can try to see how we can in those living assessment or can make those links. Yeah.
Just as a tiny provocation, I would say, well, as and I've mentioned this to Mark, as one of the few people who kept going to CERC meeting talking about SAI, I feel like the lack of a connection has not been for lack of trying on the side of GeoMIP, as much for the fact that the broader Stratospheric aerosol community for a long time has tried to keep as far away from engaging with SAI as possible. And so this is in a way been an obstacle. And I mean, this is partly why I'm so pleased that we've had this workshop these 4 days. But it wasn't because GeoMIP didn't want to be included. Mark, sorry.
I think
Yeah. I mean, maybe GeoMIP, in a way, it was included because Alan Roebuck and Claudia Timrek were always part of CERC, but there was a certain reluctance to engage in that. But I mean, all the observational tools that we used for natural analogs, volcanic eruptions, piracy bees, they're going to be relevant if SAI is ever going to be tested or even deployed. And I think, I mean, we're going to pick up in a discussion dedicated to observations on that tomorrow. And I think we've seen in this program, there was at least a talk by Frank about what the needs are. And then there was at least one talk by Anna Lange about what would the observations, how could they cope with SAI, because the plumes and the amount of aerosol would look different. And in this discussion, what I find important is if the people involved in the various assessments, like we heard about the EEAP assessment, it's part of the ozone assessment. It's also going to be a chapter in the IPCC assessment. If you talk to the community present at this workshop about the different aspects, what would you need in terms of review papers or small reports that go into detail and sort of give a summary of all the research that's already being done and that's being planned for the next few months. And maybe we can find ways to produce documents that would be helpful for you to write these assessments. I think what we don't need is that from this workshop, we say, okay, we do another WCRP assessment on SAI. That's not what we need. But I think there might be specific aspects like the observational capacities and attribution things, the uncertainties in the models, where you may want some document that give an overview of what we have learned in all the presentations. I think we've seen a very broad variety of what's being done in terms of SAI. And that's, I think with that, this workshop hopefully will be helpful in the process.
Simone and Gabriel?
Okay, so regarding the disconnect between CERC, I think there's also VolMIP, right? That's another MIP for volcanic injections or volcanic eruptions. Yes, I agree that it has been difficult. I think we can still continue trying in some way, right? I mean, maybe we can try to have a joint workshop at one point, right? Invite, somehow make it happen. I don't know how, but it is always something.
We have this workshop.
Yes, but who's here from VolMIP? Some people, or from CERC, right?
There are quite a few.
Yeah, that's great because we did learn from volcanoes. And yeah, thank you. You're right. We can continue and we're making small progress. So this is one of the things we do and we should continue doing. I agree. Mm-hmm. That's a good point. I'm just saying when Danielle says we tried, I'll just say we'll have to continue trying. That's what we need to do. It doesn't mean once we tried, we give up. But
I'm nothing but annoyed.
You didn't mean that. No. But I'm just saying.
And it's now just to make that point. SAI is now written in the new implementation plan of our activity, so we can't avoid it anymore.
Yeah, that's good. And I think really it needs time. And people will go back and forth, and there's always the resistance, of course, because we do need to address always the point that this is to study something, but we do need the governance, we do need the emission cuts, all that stuff, of course. People are worried about that. The other question I had for Jean-Paul, just real quickly, I hope, Gabriel, that's okay before you go. Yeah, so you make the point that there could be really a problem with satellites observing aerosol, but then on Monday we heard this presentation, it sounded like, we're good, we're all set. And yeah, it showed satellites that were actually not funded, like CARE, I think is, yeah, the one from Michael Höpfner. So I wonder what is the real situation, because your assessment is different than what we kind of heard from on Monday.
Yeah, no, it's very dynamical, I would say. I mean, obviously, depending very much of also because NASA has a strong contribution on stratospheric aerosol observations, and the new NASA Earth science budget in the present budget has been cut by 50%. So some of those missions, like, okay, Luce, for example, that was still discussed maybe 3 months ago, it's unlikely that's going to happen. SAGE is very much at risk right now in the new president budget. And so the reason of this kind of discrepancy is because it's the US situation, political situation, Earth science and NASA Earth science budget is changing very quickly. So
yeah, let's pick that up tomorrow in the discussion on observations.
That's right. Thank you. Yeah.
And give Gabriel maybe a chance to finally speak.
So I just wanted to, I mean, it's just a quick comment. You were talking about, providing some sort of like overview of what we learned in this workshop, right, as a basis that we can use then for the assessment reports. What about an APARC newsletter? I don't know whether that is in your plans.
That will definitely be done.
Okay.
But we also want to produce things in the scientific literature. But there will be an APARC newsletter about this workshop, an article. We can promise you that.
Thanks.
Yeah. Okay. Let's see any hands raised. So maybe I know you're gonna be discussing tomorrow, but it's gonna be 2 a.m. my time, so I wouldn't join. So I think just from my perspective, I feel like perhaps one of the outcomes and one of the things that hasn't been done before could really be an analysis of all potential analogs of SAI. What would it take to study them more in depth, or what kind of observational systems would be needed in order to study them better? And then sort of that could also provide a perspective on, well, this is the niche that could be filled by perhaps outdoor experiment, or the conclusion that there is no niche to be filled and that there is so much more. So I feel like a document like this, rather than just a set of recommendations, but a set of recommendation backed by what we know about analogs and how they could work, I think could be a really powerful and important document to have. And this is both true for surface climate as much as for radiation or stratospheric temperatures and so on, right? Because I feel like the discussion we've had and some of the figures Gabriel showed about surface climate and what Simone said, yes, of course, there's been research about sort of the Asia reduction in aerosols, and that could probably be used as what are the things that we could leverage? What are the next things that we could be looking out for that could help us understand better one piece or the other of the picture?
Yes, I think it's a great suggestion. I kind of like it a lot. I also, I mean, you may have felt it. I'm kind of try to promote as much as I can natural analogs. I think there's a lot of things we can learn, and I think summarizing some of how, I mean, you can imagine some sort of matrix. How good is an analog versus the process you are looking, and certainly there is, I think, things we can still learn, and simply we come a little bit too quickly sometimes into the conclusion that natural analogs are imperfect, and how they're imperfect. I mean, that's kind of where I think the discussion and maybe the connections with SAI is very much.
And there could also be, sorry, Simon, I saw your end, but just to conclude this, like there could also be a point there about what kind of observational systems are needed or at risk of going away that would be very useful for a potential eventual detection. Right. We mentioned a lot of missions, but another potential mission from the European Space Agency would at least pass the first stage is ECHO. It was about measuring radiative forcing. I'm actually talking to some of them, the people that are involved with ECHO on Friday about making sure that there can also be an angle about how ECHO could be used to potentially observe changes due to SAI in terms of top of atmosphere radiative forcing. ECHO would be sort of a follow-up to CIRRUS or parallel to CIRRUS. So having also some of that could be useful, because I think this is the point in which if policymakers and politics starts getting interested about SAI, the point that this community, the scientific community could make is, yeah, but you can't think about this unless you have all of these basic science done, and unless you have all of these systems in place already before you discuss things like outdoor experimentation, or even on the other hand, there's no point in banning something you don't understand, and these are the things that you need to know. Simone, want to add something?
Just to echo what you were saying, to make the point, and maybe it's all clear, but just what I think is interesting in this, something like an assessment of this, is to really relate it also to small scale experiments, because they are not perfect. They are like analogs. They are short injections of something. And that's where, I mean, you can only learn processes from field experiments, because we cannot, else it's a full implementation, especially on climate, but also on other things. If they are tiny, what do you actually learn compared to when you do, analog or other thing, if you observe analogs? And I think putting them side by side, what is the advantage of the one or the other, or can they even complement? But that's, again, you're saying tomorrow is a discussion, and yeah, I won't be there either. So maybe you can take that in the discussion tomorrow and see what other people would be great. Yeah, I think I'm just repeating, but I think it's an important point.
Okay.
Yeah.
Go, Jean-Paul.
I was just about, I mean, I'm still reluctant to some extent to put them on the same level of comparison. Especially because of there is still huge ethical aspect of even the smallest scale experiments you can do. I'm yeah, and the public perception of that from especially social sciences demonstrates or indicates that that's the public perception on SAI as and especially when we talked about small experiments is highly controversial. And so of course I mean, as scientists, I understand that we need the physical science to shed light on those processes. We cannot also neglect public perception. Is it a problem of communication? Is it a problem? But at the same time, that's really so there is more, I think, to connect with social sciences on that, especially. Maybe that's where the bridge can be, is between the natural analog and the small scale experiments, is where the social science lies. And maybe something we could discuss.
Yeah, I think that's exactly the point to make then. Why is there a difference? And maybe it's not in the physical processes. Maybe it is really in that part. And that's important to point out, I think.
Jean-Paul, I just want to make a point on that. I mean, first of all, of course, the ethical aspect, the personal ethical aspect is a different one and an important and relevant one as well. But two things on that. The first one is that, for instance, a piece like this that discusses outdoor experiment could also highlight the difference between a scientific outdoor experiment that is done transparently and publicly versus something for profit. But also, since you said you went to the you were at the RFF meeting this year, last year, Chad Baum and Ben Sovakol group presented some results that are published about the fact that if you ask people about whether they would be in favor of an experiment done by a public university, for instance, their level of agreement about, yeah, of course an experiment should go on is pretty high. It's much higher than expected. And I think ScopeX happened the way it happened and whatever, but I think that is not such a give. I'll post the paper in the chat, is the last one. But I actually think that it's partly like an experiment that were to be meaningfully scientifically justified and again transparently described could have the opportunity to actually break a big dislock between pro or against or all of that. But in general, again, this is different from just thinking about the ethical aspect or the personal opinion that one might have. So okay, Mark, and then I think we have 2 minutes to close.
Yeah, I mean, aside from the debate whether we should engage in small scale experiments or not, I think there's still a lot of research that can be done in parallel or even before small scale experiments. I mean, many of these, we have learned about alternative materials that may serve a better job than sulfate. And while sulfuric acid particles, sulfate droplets, are very well characterized in the lab for their radiative, optical, microphysical properties, for some of these materials, these measurements do not exist. We've seen some presentations that this work is being done, which I like very much. And that would go into the models. And I don't think that the models are in a state where the only way to improve the models for projections of SAI scenarios is small-scale experiments. So that research that should continue at optimal speed and all the support it can get. And then if we feel that at some point small-scale experiments are needed to find out the missing pieces of the puzzles, then the debate should start there. But I think there's still a lot of research, a lot of science that's needed aside from these small-scale experiments. Just as a comment on that. Thanks.
Yep. Okay. If there are no more intervention, I think close it for here. And
yeah, I was about to just a quick comment and a quick question for you, Daniel and Simon. It seems to me that what Mark raised is a upscale or downscaling problems, right? In most of the GeoMIP simulation, obviously, there are large-scale simulations. And so is there any effort as a part of GeoMIP or another modeling group to try to study more like upscaling part of the problem, which kind of, I think, connect the small-scale experiment to how it get dispersed and not only small scale, but could be also large scale injections. They start from single point almost, and not exactly, but certainly an area for. I mean, the injection would start from an area which is much smaller than what GeoMIP modeling activities have been doing. So what's the research that's been done on that?
I can just personally say I know there's a few groups that are researching this, like at Albany, at the University of Albany. There's something. Reflective is also spinning up a lot of work on these. on sort of the turbulence scale to diffusion to the grid box scale. Plus, there was work by Seb done on the pluming grid. So there is something that it's spinning up a bit, but as you sort of raised before, there's sort of always the problem of the moment you think a bit more deeply about this thing, you have to also engage with the question of how would you release the material, how would you deliver it, and that gets very uncomfortably close to thinking about how a real deployment would look like. So there's always been a few challenges, but I think that there's a lot of effort spinning up, and ARIA has also funded some research on this specific point. Okay.
Thank you.
If there's nothing else, I think we can thank everybody for their participation, and can close for today. And some of you will be back tomorrow.
Indeed.
Yeah,
One
thank
more session.
Thanks for hosting.
One more
3
session.
discussions.
Thank you, everybody.
Thank you all.